Hello there, and welcome to Just About Earth, a quiet corner where curiosity slows down, explanations take their time, and science unfolds gently enough to listen to while the rest of the world begins to fade into the background. Tonight, we're going to wander back farther than most stories ever go, to a time long before forests, before oceans filled with fish, before even the continents we know today are taking shape. We're going to explore a simple but surprisingly difficult question. What was Earth like when it first formed? It's a strange thing to imagine, because everything familiar to us, every mountain, every cloud, every grain of sand depends on billions of years of change. The Earth we know now is calm compared to its earliest days, stable, mostly predictable, comfortably cool at the surface, and wrapped in a sky that feels permanent. But the young Earth was none of those things. It was hotter, louder, brighter in places, darker in others, and far more chaotic than the planet we walk on today. Before we begin tracing that story, let me ask you something, just for a moment of quiet reflection. Where are you listening from right now? Perhaps you're at home, perhaps travelling, maybe lying in bed with the lights already dim. And what time is it where you are? Late evening, early morning, or somewhere in between? It's always a little fascinating to think that people scattered across the world can share the same story while standing in entirely different moments of their own day. If you find this kind of slow exploration calming, or if you simply enjoy letting your mind drift through big ideas at an unhurried pace, I'd be very grateful if you considered liking the video or subscribing to the channel. It helps this small, quiet space reach others who might also enjoy a gentle journey through science before sleep. Now let's settle in and begin, not with oceans or mountains or even land, but with a time when Earth itself did not yet exist. It's easy to picture the present-day solar system as something permanent. The sun rises, the planets orbit, the moon circles overhead, and everything feels settled, as if it has always been this way. Yet the solar system had a beginning, and it was far less orderly than the calm, clock-like motion we see now. More than 4.5 billion years ago, there was no Earth, no Mars, no Jupiter, not even the Sun as we know it today. Instead, there was a vast cloud of gas and dust drifting quietly in one of the spiral arms of the Milky Way. This cloud was cold, thin, and enormous, stretching across distances so large they're difficult to imagine. Most of it was hydrogen and helium, the simplest elements in the universe, left over from earlier generations of stars. Mixed in were tiny grains of heavier material, fragments forged long ago in stellar explosions, drifting silently in the dark. For a very long time, nothing much happened. The cloud simply existed, cold and quiet, slowly moving through space. Then something disturbed it. Perhaps a nearby star exploded, sending a shockwave rippling outward. Perhaps gravity within the cloud itself began to pull matter together unevenly. Whatever the cause, parts of that drifting cloud began to collapse inward, slowly at first, then faster as gravity gathered strength. As the material fell inward, it began to spin. This is one of those small but important rules of nature. When something contracts, it spins faster, just as a figure skater spins more quickly when pulling in their arms. Over time, the collapsing cloud flattened into a wide, rotating disk, with most of the material gathering at the centre. That central region grew hotter and denser until, eventually, temperatures and pressures became so extreme that nuclear fusion ignited. Hydrogen atoms began to fuse into helium, releasing enormous amounts of energy. The Sun was born. Around it, the rest of the disk remained, a broad, slowly rotating field of dust and rock fragments circling in the newborn star's light. Within this disk, countless tiny particles began to collide. At first, the collisions were gentle, more like grains of flour drifting together than stones striking each other. Static forces helped them stick. Small grains became pebbles. Pebbles became rocks. Rocks became boulders. Given enough time, gravity began to play a stronger role. Larger clumps pulled in smaller ones. Collisions became more energetic. Some objects shattered, others merged, and gradually over millions of years, a handful of growing bodies began to dominate their surroundings. These were the beginnings of planets, though at this stage they were nothing like the worlds we know now. They were irregular, hot, and still forming, surrounded by debris and constantly changing. Some of these early worlds would become Mercury, Venus, Earth, and Mars. Others would grow into the gas giants far beyond. But at this stage, everything was still in motion, still assembling, still uncertain, and somewhere in that swirling disk of dust and stone, one of those growing bodies was beginning to take shape. Not yet a blue planet, not yet a world of oceans and clouds, just a mass of rock, metal and heat, gradually increasing in size as more material fell inward. This was the beginning of Earth. If you could have seen it then, you might not even have recognized it as a planet. There were no continents, no seas, no atmosphere to speak of. The surface was not solid in the way we understand it. Instead, much of it was molten, glowing faintly under a sky filled with drifting debris. Impacts were constant. Pieces of rock, some small, some hundreds of kilometers across, struck the growing planet again and again. Each collision released energy, generating heat, melting rock, reshaping the surface. The young Earth was not a quiet place. It was a world in the process of becoming. It's worth pausing for a moment to consider just how much energy was involved in this process. When an object the size of a mountain strikes a planet at tens of thousands of kilometers per hour, the energy released can rival that of millions of nuclear explosions. And in those early millions of years, such impacts were not rare events. They were ordinary. The surface of the forming Earth would have glowed in places, rivers of molten rock flowing slowly across vast plains of semi-liquid crust. Above, the sky would not have been blue, but dark, filled with ash, vaporized rock, and fragments still orbiting in chaotic paths. There was no rain yet, no oceans to fall into. Water, when present, existed mostly as vapor, trapped in the thickening atmosphere or locked inside minerals deep within the planet's interior. And yet, even in that violent environment, processes were unfolding that would eventually make life possible. Heavy elements like iron were sinking toward the center, forming Earth's core. Lighter materials floated upward, forming the first crude layers of mantle and crust. Heat from impacts and radioactive decay kept the interior in motion, setting the stage for the slow churning that still drives plate tectonics today. All of this was happening long before the first microbe, long before the first drop of liquid water settled on the surface. It's strange to think about the planet this way, as something unfinished, still assembling itself piece by piece. We tend to imagine Earth as stable and complete, but in reality it has always been changing. Mountains rise and erode, oceans open and close, continents drift. Even now, the ground beneath us is not as permanent as it seems. In those earliest days, though, change was not slow and subtle. It was rapid, dramatic, and sometimes catastrophic. From time to time, truly enormous objects collided with the young Earth, reshaping it on a global scale. One of those impacts, as we'll eventually see, was so powerful that it changed the entire planet and gave Earth something that still lights our nights today. But that moment comes later in the story. For now, it's enough to picture a world still glowing in places, still gathering mass, still surrounded by the remnants of the disk from which it formed. A world without oceans, without air fit to breathe, without even a stable surface to stand on. And yet, despite the violence of those early millions of years, the processes that would eventually make Earth habitable were already underway. Gravity was organizing matter, heat was driving internal motion, chemistry was beginning to sort elements into new combinations, slowly, very slowly. The conditions that would one day allow oceans, continents, and life were taking shape. It's interesting to reflect on how long these processes took. Human history, from the earliest cities to the present day, spans only a few thousand years. The entire age of dinosaurs lasted about 165 million years, which seems immense to us. But the formation of Earth itself, from drifting dust to a recognisable planet, unfolded over tens of millions of years, and the changes that followed continued for billions more. Time on this scale is difficult to feel in any intuitive way. It doesn't pass in seconds or hours, but in slow, almost imperceptible transformations. Continents shifting a few centimetres per year, mountains rising grain by grain, planets forming particle by particle. And if you imagine standing somewhere far above the early solar system, watching it unfold in fast forward, you would see dust gathering into streams, streams into clumps, clumps into worlds, all circling a brightening sun. One of those worlds would gradually become the Earth we know. But before it could become anything like the planet we recognise, it would pass through stages far more extreme than most people realise. Periods when its surface was nearly entirely molten. Times when the sky itself was filled with fire from constant impacts. Ages when the air was thick with gases that no human could breathe. Understanding those early stages means looking not just at Earth itself, but at the environment in which it formed. The crowded, chaotic young solar system where worlds were still under construction and collisions were part of everyday planetary life. Long before the young Earth was anything like a planet, before there was ground to stand on or even a solid surface to cool, the region around the newborn sun was a crowded and restless place. It did not resemble the calm solar system we see today, with planets tracing steady, predictable paths. Instead, it was more like a vast construction zone, full of drifting material, unfinished worlds, and constant motion in every direction. To picture this properly, it helps to imagine the sun not as the stable star we know now, but as a younger, slightly more energetic version of itself. It had only recently ignited, and the disk of gas and dust left over from its formation still surrounded it, stretching billions of kilometres outward. This disk was thin compared to its enormous width, rather like a wide, flat cloud slowly turning in silence. Within that disk, tiny grains of material were moving in countless overlapping orbits. Some were no larger than specks of dust. Others were already growing into pebbles, rocks, and larger fragments. Collisions happened constantly, sometimes gentle enough that particles stuck together, sometimes violent enough to shatter them apart again. The process was messy, uneven, and surprisingly slow. Gravity, however, was patient. It does not hurry, but it never stops working. Wherever slightly more material gathered in one place, gravity pulled in more. Over time, these clumps grew larger, and as they did, their gravitational pull became stronger, drawing in nearby debris like a quiet, persistent magnet. These growing bodies are known as planetesimals, a word that sounds a bit technical, but simply means small building blocks of planets. They were the first recognisable steps toward the worlds we know today. Some planetesimals remained small, eventually becoming asteroids or comets. Others continued to grow, colliding and merging with their neighbours. Each impact released heat, melting parts of their interiors, reshaping them, sometimes breaking them apart and forcing the process to begin again. It was not a peaceful time. If you could have stood safely somewhere above this scene, you would have seen countless objects crossing paths, spiralling inward or outward, drawn by gravity into new orbits. Some collisions would have been gentle, producing only a small puff of dust. Others would have been spectacular, sending glowing fragments arcing away in all directions. Yet despite all this activity, there was also a kind of order emerging. Over millions of years, material in the disk began to separate into regions. Close to the sun, where temperatures were extremely high, only metals and rocky materials could remain solid. Ices and lighter compounds simply evaporated under the intense heat. Farther out, where it was colder, ice could survive. There, planetesimals could grow larger, accumulating frozen water, methane, ammonia, and other materials. This difference in temperature is one of the reasons the inner solar system formed rocky planets like Earth and Mars, while the outer regions gave rise to gas giants and icy worlds. At this early stage, however, none of those planets were fully formed. Everything was still in progress. It's interesting to consider how quiet this might have seemed from a distance. Space is a vacuum after all, and even enormous collisions would have unfolded in silence. No thunder, no roar, only the slow ballet of glowing fragments drifting apart, illuminated by the young sun. Time, meanwhile, was doing its slow work. Millions of years passed, then tens of millions. Gradually, certain planetesimals grew large enough to dominate their surroundings. Their gravity cleared nearby regions of smaller debris, either sweeping it up or flinging it into new orbits. These growing bodies are called protoplanets, and one of them, still incomplete and constantly reshaped by impacts, was beginning to take shape in the region that would one day become Earth's orbit. But Earth was not alone. Nearby, other protoplanets were forming as well. Some would eventually become Venus or Mars. Others would not survive, shattered by collisions or absorbed into larger neighbours. The early solar system was full of such unfinished worlds, many of which no longer exist in recognisable form. This raises a curious thought. The planets we see today are, in a sense, the survivors of a long and chaotic process. Many worlds formed and vanished before the solar system settled into its present arrangement. What remains now is only the final, relatively stable configuration that emerged after hundreds of millions of years of collisions and rearrangements. During this era, the region near the young sun would have looked very different from the orderly set of orbits we observe today. Paths crossed more often. Orbits were more eccentric, more tilted, less predictable. Gravitational interactions between growing planets constantly altered trajectories, sometimes sending objects spiralling inward toward the sun, sometimes flinging them outward into deep space. Some of those wandering fragments still exist today, in the asteroid belt between Mars and Jupiter. Many of those asteroids are remnants of planetesimals that never quite managed to assemble into a full planet, their growth interrupted by the immense gravitational influence of Jupiter, which stirred their orbits too violently for them to merge peacefully. Jupiter itself was forming during this time, and its presence had enormous consequences for the entire solar system. As it grew, its gravity acted like a giant stirring spoon, disturbing nearby regions and sending waves of motion through the disk. Objects that might otherwise have settled into stable orbits were nudged, scattered, or drawn inward toward the inner planets. This meant that the young Earth was not only growing by gathering nearby material, but was also being bombarded by objects from farther away, some of them rich in water and volatile compounds. Many scientists believe that a significant portion of Earth's water may have arrived this way, carried by icy bodies from the outer solar system. So even in these early stages, long before oceans existed, the ingredients for future seas were already being delivered, piece by piece, impact by impact. It's remarkable to think about how indirect this process was. The water in today's oceans may have begun as ice locked inside distant planetesimals, drifting in the cold outer regions of the solar system, only to be thrown inward by gravitational interactions and ultimately collide with the growing Earth. The story of Earth, in that sense, begins not just here, but across vast distances, involving materials that formed under very different conditions. Meanwhile, the sun itself was changing. Young stars are often more active than older ones, producing powerful solar winds, streams of charged particles flowing outward at high speeds. These winds gradually swept away much of the remaining gas in the protoplanetary disk, thinning it out and marking the end of the main planet-forming era. As the gas dissipated, the solar system began to clear. Collisions still occurred, but less frequently than before. Orbits slowly stabilized. The broad, dusty disk that once surrounded the sun faded, leaving behind the growing planets and smaller remnants scattered throughout the system. By this point, Earth had grown substantially, though it was still far from the stable world we know. Its surface remained extremely hot, reshaped repeatedly by impacts and internal heat. Heavy elements were still sinking toward the centre, forming the core, while lighter materials rose toward the surface. In a way, Earth was differentiating, organising itself internally, much like a liquid mixture separating into layers over time. Iron and nickel, being dense, sank inward. Silicate rocks formed the mantle. Lighter minerals floated upward, forming the earliest crust, though this crust was thin and often remelted by the constant heat below. It is difficult to overstate how different this world would have looked. There were no oceans yet, no blue sky, no green or brown or white visible from space. Instead, the surface likely glowed in places, streaked with lava flows, while above, a thick atmosphere of volcanic gases and vaporized rock hung in turbulent layers. And still, impacts continued. Some were small, leaving craters that were quickly erased by volcanic activity or new collisions. Others were enormous, capable of melting large portions of the crust, or even altering the planet's rotation and tilt. One of those impacts, far larger than most, would eventually play a defining role in shaping Earth's future. But to understand that moment fully, it helps first to appreciate just how common collisions were during this era. The early solar system was not a place where planets formed quietly and were left alone. Growth was inseparable from destruction. Worlds were built by breaking other worlds apart. There's something almost paradoxical about that. The stability we experience today, the calm landscapes and predictable seasons, ultimately grew out of a period of extraordinary violence. Without those impacts, Earth might never have grown large enough to hold an atmosphere or retain liquid water. Without the mixing of materials delivered by countless collisions, the chemistry necessary for life might never have assembled. So even the chaos had a purpose, though it unfolded blindly without intention, guided only by the laws of physics. If you imagine watching this period in accelerated time, millions of years passing in seconds, you would see a glowing, restless Earth slowly increasing in size, its surface repeatedly reshaped, its interior growing hotter and more organised, its orbit gradually stabilising as nearby debris was cleared away. Around it, other protoplanets followed similar paths, each with its own history of collisions and transformations. Some would remain intact, others would not survive, and throughout it all the sun shone steadily brighter, illuminating a system that was slowly, very slowly, beginning to resemble the one we know today. At first, the process of building a planet does not look like much at all. There are no dramatic explosions, no sudden appearances of continents or oceans, nothing that would make it obvious that a world is forming. Instead, everything begins quietly, with particles so small they would slip through your fingers unnoticed. These particles drift through space, moving slowly, occasionally colliding, sometimes sticking together. And if you could watch this process unfold in real time, it would seem almost motionless. Days would pass with no visible change. Years, centuries, even thousands of years would show only the faintest hints of growth. Yet given enough time, those tiny beginnings lead to something extraordinary. To understand how a planet like Earth forms, it helps to start with the simplest ingredients. The early solar system was filled with dust grains made of silicates, metals, and traces of ice. Many of these grains were smaller than grains of sand, some no larger than smoke particles. They orbited the sun in slightly different paths, occasionally bumping into one another. When two grains collided gently, they sometimes stuck together. This might sound surprising, but at very small scales, electrostatic forces can act like a kind of natural glue. Much like dust clinging to a television screen or socks sticking together in a dryer, these tiny particles could attach and remain joined. Once stuck together, they formed slightly larger clumps, and those clumps collided with others, gradually building aggregates that were larger and heavier. This stage is sometimes compared to snowflakes forming in clouds. Individual ice crystals drift and collide, gradually building larger, more complex structures. In space, the process was slower, but the principle was similar. Piece by piece, grain by grain, matter gathered. Over thousands of years, those aggregates grew into pebbles. Over longer stretches of time, pebbles grew into rocks. And as objects became larger, gravity began to play a role. Gravity is weak when objects are small, but it strengthens as mass increases. Once a body reaches a certain size, its gravity becomes strong enough to attract nearby material more effectively, accelerating its growth. This stage is often called runaway growth, because the larger an object becomes, the faster it grows compared to its smaller neighbours. Imagine a crowded field of rolling snowballs. The slightly larger ones gather more snow as they roll, becoming larger still, which allows them to gather even more. Eventually, a few large snowballs dominate the field while many smaller ones remain scattered. Something similar happened in the early solar system. Within the disk of debris surrounding the Sun, certain regions began producing larger bodies faster than others. These bodies swept up nearby material, clearing their immediate surroundings and growing into planetesimals tens or even hundreds of kilometers across. At this size, the collisions between objects became much more energetic. When two bodies several kilometers wide collide, the energy released is immense. Sometimes the objects merged, forming a larger body. Sometimes they shattered, producing clouds of debris that would later reassemble into new objects. Growth was not smooth or predictable. It was chaotic, filled with setbacks and sudden leaps forward. It's worth pausing here to consider how much time this required. From the first microscopic grains to bodies tens of kilometers wide, the process may have taken a few million years. That might sound like a long time, but in cosmic terms it is relatively quick. Once planetesimals formed, the next stage began. These larger bodies started colliding with one another, merging into protoplanets hundreds or thousands of kilometers across. Gravity now dominated the process. Instead of random drifting, objects were pulled together by mutual attraction, spiraling inward and merging in dramatic impacts. With each collision, enormous amounts of heat were released. Rock melted, surfaces became molten, interiors grew hotter as radioactive elements decayed, releasing energy trapped deep within the growing planet. At some point, a protoplanet reaches a size where its internal heat becomes so intense that much of its interior turns liquid. When this happens, another important process begins, one that shaped the structure of Earth as we know it today: differentiation. Differentiation is the separation of materials by density. When rock is molten, heavy elements like iron and nickel sink toward the center, while lighter materials float upward. Over time, this creates layers, a dense metallic core, a thick mantle of silicate rock, and eventually a crust of lighter material at the surface. This process is similar to what happens when oil and water separate in a bottle, though on a vastly larger and hotter scale. Earth underwent this process early in its history. As it grew larger and hotter, iron sank inward, forming the core that still generates Earth's magnetic field today. That magnetic field, invisible but vital, protects our planet from harmful solar radiation and helps preserve the atmosphere. It's remarkable to think that this protective shield, which makes life possible, began forming during a time when the planet itself was still molten and unrecognizable. Meanwhile, the surface of the growing Earth was far from stable. Lava oceans may have covered vast regions. Impact continued, sometimes large enough to melt significant portions of the crust. Volcanoes released gases trapped within the interior, gradually building an atmosphere, though it was very different from the one we breathe today. This early atmosphere likely contained water vapor, carbon dioxide, methane, ammonia, and other gases, but almost no oxygen. The sky would not have been blue. It may have appeared hazy, reddish, or orange, lit by a sun that shone through thick layers of vapor and dust. If someone could have stood there, which of course would have been impossible, they would have seen a landscape dominated by glowing rock, erupting volcanoes, and a sky filled with drifting clouds of steam and ash. it would not have felt like a world ready for life. Yet even in these extreme conditions, important changes were unfolding. As impacts became slightly less frequent and the surface began to cool in places, the first thin crusts formed. These crusts were fragile and often remelted, but they represented the first steps toward a solid surface. Water vapour released by volcanic activity accumulated in the atmosphere. Over time, as the planet cooled further, some of that vapour would eventually condense, forming clouds and rain, though this stage was still far in the future. Another subtle but important change was occurring in the planet's orbit. As Earth gathered most of the material in its immediate region, fewer large objects remained to collide with it. The solar system itself was gradually becoming less chaotic, though enormous impacts were still possible, and one of those impacts would soon change everything. But before we arrive at that moment, it's worth reflecting on how extraordinary the process of planet formation really is. A world like Earth begins as dust, invisible grains drifting in darkness. Through countless collisions guided only by gravity and the laws of physics, those grains assemble into rocks, rocks into mountains, mountains into continents. Every ocean, every valley, every living creature owes its existence to that long chain of events. It is easy to think of planets as permanent objects, solid and unchanging, but in truth they are the result of continuous processes shaped by heat, gravity, chemistry and time. Even now, Earth is still evolving, though much more slowly than in its earliest days. The continents drift, mountains rise and erode. The interior continues to churn, driven by heat left over from formation and radioactive decay. The story of Earth did not end when the planet formed. In many ways, that was only the beginning. Not long after the young Earth had begun to take on the rough shape of a planet, the environment around it was still far from peaceful. Space near the inner solar system remained crowded with unfinished worlds, drifting fragments, and bodies large enough to reshape entire planets if they struck with the right angle and speed. The Earth was growing, cooling in places, and organising itself internally, but it was still living through what scientists sometimes call the era of heavy bombardment, a time when impacts were not rare disasters but a normal part of planetary life. To understand just how violent this period was, it helps to imagine the sky, not as empty or calm, but as busy. Not filled with clouds or birds, of course, but with countless objects moving silently through space, each tracing its own orbit around the sun. Some were no larger than boulders, others were the size of mountains. A few were entire protoplanets, worlds in their own right, still assembling and still wandering slightly unstable paths. Every one of those objects carried enormous energy simply because of how fast it was moving. In the inner solar system, orbital speeds are measured in tens of kilometers per second. When two bodies collide at those speeds, the energy released is almost beyond comprehension. Rock does not merely crack or shatter under such conditions. It melts, vaporizes, and sometimes explodes outward in expanding clouds of incandescent debris. The early Earth endured countless impacts like these. Some left craters that would later be erased by volcanic activity or remelting. Others were powerful enough to melt large portions of the crust, turning solid ground back into molten rock. There may have been times when much of the planet's surface was covered by a global magma ocean, glowing faintly under a dark, hazy sky. It is difficult to picture a world like that because nothing on modern Earth truly resembles it. Even our largest volcanic eruptions, impressive as they are small compared to the forces at work in those early collisions. The scale was planetary. Entire regions could be reshaped in a matter of hours. And yet, for all the destruction, these impacts also played a crucial role in shaping the Earth into a stable, layered planet. Each collision added mass. Each merging body contributed new material, new elements, new heat. Growth and violence were inseparable. There is also an interesting detail about impacts that is easy to overlook. Not every collision was a direct head-on strike. Many occurred at angles, glancing blows that sent material spiralling into space or redistributed it across the surface. Some of this debris fell back to Earth. Some escaped into orbit, forming temporary rings that slowly dispersed. A few fragments may have been thrown far enough to become independent objects for a time before eventually falling back. If you could have watched the young Earth from a safe distance, you would have seen flashes of light marking impacts, plumes of molten rock rising and spreading, and the surface slowly reshaping again and again. There would have been no quiet nights, no long periods of stillness, only intervals between collisions, sometimes thousands of years, sometimes far shorter. During this period, heat dominated everything. Heat from impacts, heat from radioactive decay deep within the planet, heat from the compression of materials under gravity. The interior of the Earth was extremely active, convecting and churning as dense materials sank and lighter ones rose. Volcanoes were likely far more numerous than today, releasing vast quantities of gas into the atmosphere. That early atmosphere was thick, hot and toxic by modern standards. Carbon dioxide, sulfur dioxide, water vapour, and other volcanic gases filled the air. There was no oxygen to breathe, no ozone layer to shield the surface from ultraviolet radiation. Sunlight filtering through this atmosphere may have given the sky a reddish or orange tint, dimmed by haze and ash, and still the bombardment continued. One reason this period was so violent lies in the nature of planetary formation itself. As protoplanets grew, their gravitational influence increased. This altered the orbits of nearby objects, sometimes destabilizing them and sending them inward toward the Sun or outward into the asteroid belt. Regions of the solar system became gravitationally stirred, like a pot being gently but continuously shaken. Jupiter, already forming in the outer solar system, played a particularly important role. Its immense gravity disturbed countless smaller bodies, scattering some inward toward the inner planets. Many of these objects eventually crossed Earth's path. In this sense, the young Earth was not just enduring random impacts. It was part of a dynamic system in which the movements of distant planets influenced the rate and intensity of collisions close to the Sun. There is something quietly fascinating about this chain of cause and effect. A growing giant planet hundreds of millions of kilometers away could alter the path of a rocky body, which millions of years later might collide with the Earth, delivering heat, minerals, or even water that would shape the future of the planet. Events separated by vast distances and times were linked in ways that only gravity could arrange. As the impacts continued, the surface of the Earth went through cycles of melting and cooling. When a large collision occurred, the heat released could melt extensive regions, erasing earlier features and resetting the geological record. This is one reason so little direct evidence remains from the earliest chapters of Earth's history. The rocks that formed then were often destroyed or transformed by later events. The planet was, in a sense, constantly rewriting its own surface. Despite this, some of the most important internal structures of Earth were becoming firmly established. The core had largely formed by this stage, with iron and nickel concentrated at the centre. The mantle above it was convecting slowly, transferring heat upward. The earlier stable crusts, though thin and fragile, were beginning to appear in patches. It is interesting to think about how thin that first crust may have been. Compared to the thick continental plates we know today, it was likely delicate, easily broken or remelted by new impacts or rising magma. The surface of the Earth at this time was not a permanent landscape, but something more temporary, changing over thousands or millions of years. Meanwhile, above this unstable surface, the sky itself would have looked unfamiliar. Without oceans to moderate temperature, the atmosphere may have been filled with towering clouds of steam and ash. Lightning might have been frequent, driven by volcanic eruptions and thick atmospheric layers. Meteors, far more common than today, would have streaked across the sky regularly, some burning up, others striking the ground with explosive force. Night and day would still have existed, of course, but nights would not have been as dark as they are now. Large impacts can produce glowing plumes and molten ejecta that remain luminous for hours. The horizon might sometimes have glowed faintly, illuminated by distant eruptions or fresh impact sites. All of this may sound overwhelmingly hostile, and in many ways it was. Yet it was also a time of preparation, a period when the raw materials and structures necessary for a habitable world were being assembled. The elements that make up Earth's crust, oceans and atmosphere were being mixed and redistributed. Volcanic gases were building the first substantial atmosphere. Water delivered by icy bodies or released from minerals was accumulating in the air as vapour, waiting for temperatures to drop enough for condensation to begin. Even the rotation of the planet, the length of its day, and the tilt of its axis were influenced by collisions during this time. Impacts can alter a planet's spin, sometimes dramatically. Earth's present rotation and axial tilt are partly the result of these early events. And then there were the largest collisions of all, the ones that did not merely reshape the surface but changed the entire planet. One of those collisions involved a body roughly the size of Mars, a protoplanet travelling on an orbit that intersected Earth's path. This object, often called Theia in modern reconstructions, was not a small asteroid but a world in its own right, with its own history of formation and heating. When it approached the Earth, the encounter was not a gentle meeting. The two bodies collided at an angle, releasing energy so immense that large portions of both worlds were vaporized or melted instantly. Debris was blasted into orbit, forming a vast ring of molten and vaporized rock around the Earth. Over time, that ring would cool and coalesce, eventually forming the Moon. But that part of the story deserves careful attention in its own time, because it changed not only the appearance of the sky, but also the stability of Earth's rotation, the strength of its tides, and possibly even the conditions that allowed life to develop later. For now, it is enough to recognise that collisions of truly enormous scale were still possible during this era. The young Earth lived through events that would be unimaginable today, impacts powerful enough to reshape continents that did not yet exist and alter the entire structure of the planet. Gradually, however, the frequency of such impacts began to decline. As the solar system evolved, many of the remaining planetesimals were either absorbed into larger bodies, flung into distant orbits, or ejected from the system entirely. The environment around Earth slowly became less crowded, less chaotic. The change was not sudden. It unfolded over tens of millions of years. But the trend was clear. The age of constant bombardment was beginning to ease, allowing longer intervals of relative calm. During those intervals, the surface could cool more thoroughly. The crust could thicken. Water vapour in the atmosphere could begin to condense, forming the first rains, though at this stage those rains would have fallen onto hot, unstable ground, sometimes evaporating again almost immediately. Still, the direction of change was set. The planet was slowly transitioning from a molten, heavily bombarded world to something slightly more stable, though still very different from the Earth we know today. It is remarkable to think that every ocean, every mountain range, every forest and field owes its existence to this chaotic beginning. Without the impacts that built the planet and mixed its materials, without the heat that drove differentiation and volcanic outgassing, Earth might have remained a smaller, drier, less dynamic world. Violence in this case was part of creation. If you step outside on a clear night and look up, the moon appears calm, steady, almost permanent. It hangs in the sky with such quiet familiarity that it is easy to imagine it has always been there, unchanged, patiently circling the Earth since the beginning of time. Yet the moon has a beginning, and that beginning was anything but calm. To understand how the moon formed, it helps to return to the era when Earth itself was still young, still hot, and still surrounded by the lingering debris of planet formation. The solar system at that time was not the orderly arrangement we know now. Orbits were less stable, collisions were more frequent. and several protoplanets still wandered the paths that sometimes crossed. One of those worlds was a body roughly the size of Mars. Today, scientists often refer to it by the name Theia, though that name is simply a convenient label for something we can never observe directly. It was a young planet, formed from the same disk of dust and rock as Earth, circling the Sun on its own orbit, not yet part of any larger world. For millions of years, Earth and this neighbouring protoplanet travelled through space on paths that occasionally brought them near one another. Gravitational interactions between growing planets gradually altered those orbits, nudging them, shifting them, sometimes making them more eccentric or tilted. Eventually the paths of Earth and this Mars-sized body intersected at just the wrong moment. The collision that followed was not a head-on crash, in the way we might imagine two cars colliding on a road. It was more like a glancing blow, an oblique impact at enormous speed. Even so, the energy released was almost beyond comprehension. Entire regions of both worlds were instantly melted or vaporized. Rock behaved like liquid. Metal flowed. Vast plumes of molten and vaporized material were blasted outward into space. For a brief time, the Earth was transformed again into something like a global ocean of magma. The surface glowed. The atmosphere thickened with vaporized rock and gases released from the interior, and above the planet a great cloud of debris spread outward, forming a broad disk of material orbiting the Earth. This disk was not made of dust alone. It contained droplets of molten rock, fragments of crust and mantle, and clouds of silicate vapour. Heated by the violence of the impact, much of it glowed faintly, forming a ring of incandescent material circling the battered planet. Over time, gravity began to reshape this debris. Particles collided and stuck together. Larger fragments attracted smaller ones. Gradually, within that orbiting disk, a new body began to assemble. That body would become the Moon. The process was not instantaneous. It likely took thousands of years, perhaps longer, for the debris to gather into a single large object. During that time, the newborn Moon would have been much closer to Earth than it is today, appearing enormous in the sky, many times larger than the Moon we see now. If anyone could have stood on Earth's surface during those early days, which of course was impossible, they would have seen a sight unlike anything in the modern world. The Moon would have filled a large portion of the sky, glowing with heat, its surface still partly molten. Tidal forces between the two bodies would have been far stronger, raising immense tides in any molten or liquid regions of Earth's surface. It is difficult to overstate how important this event was. The formation of the Moon changed the Earth in several lasting ways. First, the collision altered Earth's rotation. Before the impact, the young planet may have spun at a different rate. The transfer of angular momentum during the collision helped set the length of Earth's day, though the day was still much shorter than it is now, perhaps only 5 or 6 hours long. Second, the impact influenced Earth's axial tilt, the angle at which the planet's axis is inclined relative to its orbit. That tilt is responsible for the seasons we experience today. Without it, Earth's climate might have been very different, possibly less stable over long periods. Third, and perhaps most importantly, the presence of a large moon stabilizes a planet's tilt over time. Without the Moon, Earth's axis might wobble more dramatically, leading to extreme and unpredictable climate shifts. The steady rhythm of seasons that has allowed life to thrive for millions of years may depend in part on that distant, silent companion. There is something quietly remarkable about that idea. The calm, predictable cycles of nature that shape forests, oceans, and ecosystems may trace back to a single violent collision billions of years ago. The Moon itself also carries a record of that ancient event. Its composition is strikingly similar to Earth's outer layers, supporting the idea that it formed largely from material blasted away during the impact. Yet it contains less iron than Earth, consistent with the idea that most of the metal from both bodies had already sunk into their cores before the collision. In a sense, the Moon is made mostly of what was once the outer part of a young planet, reshaped and gathered into a new world. As the newly formed moon orbited Earth, tidal forces between the two bodies began to change their relationship. The moon slowly moved farther away, a process that continues even today at a rate of a few centimetres per year. Long ago it was much closer, and its influence on Earth's tides was far stronger. Those early tides may have played an important role in shaping the planet's surface and, much later, in creating environments where the chemistry of early life could develop. Shallow tidal pools repeatedly flooded and exposed may have provided conditions favourable for complex molecules to form and interact. Of course, that stage of the story lay far in the future. At the time of the moon's formation, Earth was still a harsh and inhospitable place, with a hot surface, a thick atmosphere of volcanic gases, and frequent impacts continuing to reshape the landscape. Yet the frequency of the largest collisions gradually declined. Many of the remaining large bodies in the inner solar system had already merged or been scattered away. The era of giant impacts was drawing to a close. Those smaller impacts would continue for hundreds of millions of years. Meanwhile, the Earth itself was beginning to cool more steadily. The global magma ocean slowly solidified in places, forming thicker and more stable crust. Volcanoes still erupted frequently, releasing gases and heat, but the surface was no longer entirely molten. Water vapour in the atmosphere continued to accumulate. As temperatures gradually dropped, conditions were approaching the point where liquid water could exist on the surface for longer periods. Clouds thickened. Rain began to fall, at first evaporating quickly on hot ground, but eventually lasting longer as the planet cooled further. It is interesting to think about how different the sky would have looked during this time. The moon, still much closer than today, would have dominated the night, its surface brighter and more rugged, marked by the scars of its own early bombardment. The Earth, seen from the moon, would have appeared larger than the moon appears to us now, a glowing world slowly cooling under a hazy atmosphere. The relationship between the two worlds, born from violence, was already shaping their futures. There is also a broader perspective to consider. The formation of large moons like Earth's is not guaranteed for every planet. Mars has only 2 tiny moons, likely captured asteroids. Venus has none. Mercury has none. Earth's moon is unusually large compared to the size of its planet, and that makes our world somewhat unusual in the solar system. This raises an intriguing possibility. The presence of the moon may have been one of several factors that helped make Earth a stable environment for life over billions of years. Without it, the history of the planet might have unfolded very differently. Yet at the time of its formation, none of that was certain. The young Earth was still recovering from the enormous impact, still cooling, still reshaping its surface and atmosphere. The moon was still close, still slowly receding, still marked by fresh scars from impacts that struck both worlds. The solar system itself was continuing to evolve. The giant planets were settling into more stable orbits. The remaining debris was being cleared or scattered. The rate of impacts on Earth was gradually declining, though the sky was still far from empty. Long after the collision that created the moon, the Earth did not immediately become the calm, blue world we know today. The violence of that impact had left the planet profoundly changed. Much of the surface had melted. Vast regions of rock had been heated until they behaved like thick glowing liquid, and the atmosphere above was dense with vaporized material, steam, and volcanic gases. For a time, the young Earth was not a world of land and sea, but a world of fire, an immense, slowly cooling ocean of magma stretching across much of the planet's surface. It's not easy to picture a landscape like that, because nothing on modern Earth truly resembles it. Even the largest lava flows we see today, impressive as they are small compared to what likely existed then. Instead of rivers of lava winding through valleys, there may have been entire regions where molten rock extended to the horizon, glowing dull red in some places, brighter orange in others, slowly shifting and convecting under a sky thick with clouds of steam and ash. The heat that maintained this molten state came from several sources. The giant impact itself had released enormous energy, melting large portions of the crust and mantle. Radioactive elements inside the planet continued to decay, releasing heat deep within the interior. And impacts, though less frequent than before, were still common enough to add bursts of energy to the surface. All of this meant that cooling was a slow process. Rock does not lose heat quickly on a planetary scale. Even when the surface begins to solidify, the interior can remain molten for vast stretches of time, feeding new eruptions and remelting crust that has only recently formed. If you imagine the Earth at this stage, it would have looked very different from space. Instead of blue oceans and white clouds, much of the visible surface may have glowed faintly, especially on the night side, where the absence of sunlight would allow the heat of molten rock to be seen more clearly. The atmosphere, rich in volcanic gases and water vapour, would have scattered light in unfamiliar ways, giving the planet a hazy, dim appearance. Above this glowing world, the moon would have appeared enormous, far closer than it is now, its own surface still hot in places, marked by fresh scars from impacts. Tidal forces between the two bodies would have been strong, pulling at the molten and semi-molten surface of Earth, creating slow, subtle bulges in the magma ocean. It is interesting to consider that tides, which today gently raise and lower the oceans, may once have influenced seas of molten rock. At the surface, the magma itself would not have been uniform. Different minerals melt at different temperatures, and as the planet slowly cooled, crystals would begin forming within the molten material, gradually changing its composition. Lighter minerals tended to float upward, while denser ones sank, a continuation of the differentiation process that had already shaped the planet's interior. Over time, these processes would lead to the formation of the earliest crust, thin and fragile at first, forming like a skin over the molten interior. But this crust was not stable. Heat from below and impacts from above often broke it apart or melted it again. The surface of the Earth at this stage was constantly changing, solidifying in one region while breaking open in another. Meanwhile, enormous amounts of gas were being released from the planet's interior. Volcanoes were everywhere, far more numerous and active than any seen today. Each eruption released water vapour, carbon dioxide, sulfur compounds, and other gases into the atmosphere. This process, known as outgassing, gradually built the first substantial atmosphere of the Earth. That atmosphere was thick, hot, and toxic by modern standards. Oxygen was almost entirely absent. Instead, the air was dominated by carbon dioxide, nitrogen, steam, and traces of methane and ammonia. The sky would not have been blue. Depending on the thickness of clouds and volcanic haze, it may have appeared orange, brown, or grey, lit by a sun that was slightly dimmer than it is today, but still powerful enough to illuminate the turbulent clouds. Rain, when it began to fall, did not behave as it does now. Water vapour condensing in the atmosphere produced intense storms, but much of the rain that reached the surface would have struck hot rock and boiled away again, returning to the atmosphere in great columns of steam. This cycle repeated countless times, a planet-wide process of evaporation and condensation that continued until temperatures dropped enough for liquid water to remain on the surface for longer periods. It is remarkable to think that the oceans we know today may have begun as steam, circulating endlessly between sky and molten ground, waiting for the planet to cool just enough for water to settle and remain. Another important process was taking place deep within the planet. The core, already formed from sinking iron and nickel, remained extremely hot and dynamic. Movements in the liquid outer core began generating a magnetic field, though its strength and stability in those early times are still subjects of scientific investigation. That magnetic field would eventually become crucial in protecting the atmosphere from being stripped away by the solar wind. Without it, the history of Earth might have been very different, perhaps more like that of Mars, which lost much of its atmosphere over time. The surface environment during the magma ocean stage was harsh, but it was not static. Gradual cooling allowed larger regions of crust to survive for longer periods. Volcanoes built temporary landforms that sometimes persisted for thousands or millions of years before being reshaped or buried. In places where the crust thickened, the first hints of something resembling continents may have begun to appear, though they would have looked nothing like modern land masses. These early crustal fragments were small, unstable, and constantly changing, but they mark the beginning of a process that would, over billions of years, lead to the formation of continents and mountain ranges. Above all, time was the most important factor. Cooling a planet takes patience measured in millions of years. Each century made almost no visible difference, but over long stretches of time, the changes became profound. Temperatures fell. The atmosphere gradually thinned as some gases condensed or were locked into minerals. Water began to accumulate in low regions, forming the first persistent bodies of liquid. The planet slowly moved away from its most extreme conditions towards something more stable. Yet stability did not arrive all at once. Impacts continued to occur, sometimes large enough to melt portions of the surface again. The solar system still contained many wandering fragments, and Earth remained a target. Even so, the overall trend was clear. The era of global magma oceans was ending. Larger and more stable crustal regions were forming. Rain lasted longer before evaporating, clouds thickened. The surface, once dominated by glowing rock, was beginning to darken as solid material spread. It is worth reflecting on how delicate this transition was. If the Earth had remained slightly closer to the Sun, temperatures might have stayed too high for water to condense, as appears to have happened on Venus. If it had formed farther away, water might have remained frozen for much longer. The balance of distance, atmosphere, and internal heat created conditions that allowed liquid water to persist, a key step toward the development of life. But at this stage, life was still far in the future. The planet was only just becoming a place where stable oceans could exist, and many changes still lay ahead. The first true oceans would not appear overnight. They would form gradually, fed by rain that fell for thousands or perhaps millions of years, filling basins in the cooling crust. Those early oceans may have been hot, rich in dissolved minerals and stirred by frequent volcanic activity. At some point after long ages in which much of the planet's surface glowed and shifted like a slow-moving sea of fire, something new began to happen. It did not occur everywhere at once, and it did not happen quickly enough to notice from one generation to the next, even if there had been anyone there to watch. But gradually, patiently, the outermost layer of the Earth began to cool enough for solid ground to appear and remain in place for longer stretches of time. This was the beginning of the first crust. To understand why this mattered so much, it helps to think about what cooling really means on a planetary scale. When a pot of soup cools on a kitchen counter, the surface temperature drops in minutes. When a lava flow cools on modern Earth, it may take days or weeks for the surface to harden and months or years for the interior to fully solidify. But when an entire planet is hot, the amount of heat involved is enormous, and the cooling process unfolds over millions of years. The earlier solid surfaces on Earth likely formed like a thin skin on molten material beneath, somewhat similar to the way ice forms on a pond while liquid water still moves below. At first, these solid layers were fragile. Heat rising from the interior could melt them again. Impacts from falling debris could shatter or bury them. Volcanic eruptions could pour new molten rock across them, erasing any earlier features. So the first crust was not a single continuous shell. It was patchy, temporary, forming in one place while breaking apart in another. Regions of solid rock might last thousands of years, perhaps longer, before being reshaped again. Over time, though, as the overall temperature of the planet slowly declined, those patches began to survive for longer periods. It is interesting to imagine what those earlier solid surfaces might have looked like. They were probably dark, rough, and uneven, composed mostly of basaltic rock formed from cooling lava. There were no soils, no sediments, no layers built by rivers or wind. The rock would have been fresh, sharp and largely unweathered, broken only by cracks formed as it cooled and contracted. Above this surface, the sky would still have been thick with volcanic gases and steam. Clouds were not yet the familiar white shapes we see today, but heavy layers of vapour and ash, constantly shifting as heat rose from below. Lightning may have been frequent, driven by turbulent atmospheric conditions and the enormous energy still escaping from the planet's interior. Rain had begun to fall by this stage, but it behaved differently than it does now. When water droplets struck hot ground, they often flashed back into steam. In some regions, rain may have fallen for years at a time, only to evaporate again and rise back into the atmosphere, repeating the cycle endlessly. This repeated pattern of condensation and evaporation played an important role in cooling the planet. Water is very effective at carrying heat away, and every time steam rose, condensed and fell again, it helped transport heat from the surface into the atmosphere and eventually into space. Meanwhile, beneath the forming crust, the mantle remained in motion. Even today, the mantle moves slowly, driven by convection currents as hot material rises and cooler material sinks. In the early Earth, these movements were faster and more vigorous because the planet contained far more internal heat. These currents placed stress on the thin crust above, cracking it, pushing it upward in some places, pulling it apart in others. The earliest tectonic activity may have begun during this time, though it likely looked very different from the plate tectonics we see today. Instead of large, stable plates moving over millions of years, the surface may have been broken into many smaller fragments, shifting and recycling rapidly. Volcanoes were everywhere. They were not isolated mountains like many of the volcanoes we see now, but widespread openings where magma could reach the surface. Some eruptions may have continued for centuries, pouring out vast quantities of lava that spread across the landscape, creating new rock and burying older surfaces beneath. Each eruption also released gases trapped within the Earth's interior. Water vapour, carbon dioxide, nitrogen, sulfur compounds, and other gases accumulated in the atmosphere, gradually increasing its density. This early atmosphere helped trap heat, slowing the rate at which the planet cooled, but it also provided the raw materials for future oceans and chemical reactions that would become important much later. As the crust thickened in places, something else began to happen. Liquid water started to remain on the surface for longer periods instead of boiling away immediately. Small pools may have formed in low areas, lingering long enough to interact with the surrounding rock. Water began dissolving minerals, carrying them away, and depositing them elsewhere. These were the earlier steps of erosion and sedimentation, processes that would later shape landscapes on a grand scale. It is easy to overlook how important solid ground really is. Without a stable crust, there can be no persistent oceans, no long-lasting rivers, no environments where complex chemistry can unfold over extended periods. The formation of the crust marked a turning point, even though the world was still harsh and unstable by modern standards. At this stage, the moon still loomed large in the sky, closer than it is now, raising stronger tides in any bodies of liquid water that existed. The gravitational interaction between Earth and Moon was slowly changing both worlds. Earth's rotation was gradually slowing, lengthening the day little by little, while the Moon moved slowly outward. Night on the young Earth would have looked different from anything familiar. The Moon would have appeared enormous, and the sky, thick with clouds of vapour, might have glowed faintly from volcanic activity or distant lava fields. Meteors were still more common than they are today, streaking across the sky and occasionally striking the surface. Even as the crust formed, impacts had not entirely ceased. Smaller bodies continued to collide with Earth, sometimes punching through the thin crust and releasing fresh lava. These events were less frequent than in earlier ages, but they were still powerful enough to reshape regions of the surface. Over long stretches of time, however, the balance shifted. Cooling began to outpace heating in many areas. Larger sections of crust survived without being remelted. Basins formed where water could collect. The planet was slowly moving toward a state where oceans could exist on a lasting basis. There is something quietly remarkable about this transformation. The solid ground beneath our feet today, the continents and ocean floors, trace their origins back to these early stages when the first crust began to form and stabilize. Every mountain range, every canyon, every plain is part of a story that began when molten rock first cooled into solid stone. Yet the early crust was not like the continents we know now. Modern continental crust is relatively light and thick, composed of granitic rocks that formed through complex geological processes. The earliest crust was likely thinner and denser, more similar to the basaltic crust found today beneath the oceans. The formation of true continents would come much later, after long cycles of melting, recycling, and differentiation. During this era, the planet was still restless. Heat from the interior continued to drive volcanic activity. The atmosphere remained thick and heavy. Storms may have been intense, with rain falling over landscapes still shaped by recent lava flows. And still, time moved forward, slowly but steadily. Millions of years passed. The crust thickened in places. Water accumulated in larger and more stable bodies. Chemical interactions between water, rock, and atmosphere became more complex. These interactions were quietly preparing the stage for one of the most important developments in Earth's history, though at the time nothing about it would have seemed remarkable. Simple molecules dissolved in water, reacting, combining, breaking apart, and recombining in countless ways. Energy from volcanic heat, lightning, and ultraviolet radiation drove these reactions forward. And the conditions for those oceans were now slowly, almost imperceptibly, coming into place as the crust strengthened, the atmosphere thickened, and the cycle of rain and evaporation continued, gradually tipping the balance toward a world where water could finally remain. Long before the sky turned blue, before clouds drifted in familiar white layers, and before the air carried the scent of rain or forests, the atmosphere surrounding the young Earth was thick, heavy, and almost unrecognizable by modern standards. It was not a place where wind carried the sound of leaves or where sunlight filtered gently through scattered clouds. Instead, the air was dense with vapor, gases released from the interior of the planet, and fine particles of ash and dust that drifted slowly through turbulent currents high above the surface. To understand how this earliest atmosphere formed, it helps to step back and think about what a planet's atmosphere really is. Air does not simply appear, it must come from somewhere. In Earth's case, the first atmosphere was built gradually through a process known as outgassing, the release of gases trapped inside the planet during its formation. When the Earth was still largely molten, enormous amounts of gas were dissolved in the magma beneath the surface. As that magma rose and erupted through countless volcanic openings, those gases escaped into the air. Water vapor, carbon dioxide, nitrogen, sulfur compounds, and traces of methane and ammonia poured into the atmosphere, building a thick envelope around the planet. At the same time, impacts from comets and water-rich asteroids delivered additional volatile materials. These objects, formed in colder regions of the solar system, carried ice and organic compounds. When they struck the Earth, the intense heat of impact vaporized much of this material, adding further water vapor and gases to the growing atmosphere. The result was an environment very different from the one we know today. Oxygen, which now makes up about 21% of our air, was almost entirely absent. The earliest atmosphere would have been dominated by carbon dioxide and nitrogen, along with vast amounts of steam. The sky, if one could have seen it clearly through the haze, would not have appeared blue. The blue colour of today's sky comes from the scattering of sunlight by oxygen and nitrogen molecules in a relatively clear atmosphere. In a sky filled with steam, volcanic ash, and thick clouds, sunlight would have been filtered and dimmed, giving the sky a muted reddish or brownish tone. The air itself would have been hot and heavy. Temperatures near the surface were still elevated from the planet's recent molten state, and the greenhouse effect created by carbon dioxide and water vapour trapped heat efficiently. Clouds formed high in the atmosphere, but they were not gentle drifting formations. Instead, they were massive, dense layers of steam, constantly forming and collapsing as rising heat drove powerful convection currents. Lightning may have been frequent, generated by turbulent clouds and volcanic plumes rising from the surface. Storms would have been intense, driven by temperature differences and the constant movement of heat upward from the planet's interior. Rain began to fall during this period, but it behaved differently than rain today. Much of it fell onto hot rock and evaporated almost immediately, rising back into the atmosphere in columns of steam. This cycle repeated countless times, a planet-wide system of evaporation and condensation that gradually helped cool the surface. Over long stretches of time, as the crust thickened and temperatures dropped, some of that rain began to remain on the surface longer. Small pools formed, then larger ones, eventually leading to the first persistent bodies of liquid water. But during the earlier stages, the atmosphere was still dominated by steam, and the surface was still too hot in many places for water to remain for long. Volcanoes played a central role in shaping this atmosphere. The early Earth was far more volcanically active than it is now. The interior contained much more heat, and the crust was thinner and easier for magma to break through. Instead of isolated volcanic mountains, there may have been vast regions where lava flowed almost continuously, releasing enormous amounts of gas into the air. Each eruption contributed to the growing atmosphere, and over millions of years the cumulative effect was profound. The planet, once surrounded by little more than a thin veil of vaporized rock and gases from impacts, developed a dense and persistent atmosphere capable of sustaining clouds, storms, and eventually rain that lasted. It is interesting to consider how different the Sun appeared through this atmosphere. The young Sun itself was slightly dimmer than it is today, producing perhaps 70 to 75% of its current brightness. Yet the thick greenhouse atmosphere of early Earth trapped enough heat to keep the planet warm, preventing the surface from freezing despite the fainter sunlight. Sunlight reaching the surface would have been filtered through layers of cloud and haze, producing a dim, diffuse glow rather than sharp shadows. The sky may have remained overcast for long periods, with the sun appearing as a pale, blurred disk behind thick clouds. At night, the moon would still have been a dominant presence, larger in the sky than it is now, reflecting what sunlight managed to penetrate the atmosphere. Meteors were more common, occasionally streaking through the clouds and sometimes reaching the surface in fiery impacts. The chemistry of this early atmosphere was also very different from what we experience today. Without oxygen, many chemical reactions occurred in ways unfamiliar to modern environments. Ultraviolet radiation from the sun, not yet blocked by an ozone layer, reached the upper atmosphere and drove complex chemical reactions, breaking apart molecules and allowing new compounds to form. Some of these reactions produced organic molecules, simple carbon-based compounds that would later play a role in the emergence of life. Lightning, volcanic heat, and ultraviolet radiation all provided energy to drive these processes, creating a dynamic and chemically active atmosphere. Meanwhile, water vapour continued to accumulate. Over time, as cooling progressed, clouds thickened and rainfall became more persistent. The first long-lasting rains may have lasted thousands or even millions of years, gradually filling low regions of the crust and forming the earliest oceans. These early oceans were likely hot and rich in dissolved minerals, stirred by frequent volcanic activity and impacts. The atmosphere above them remained thick with carbon dioxide and nitrogen, creating a greenhouse environment that kept temperatures relatively stable despite the faint young sun. It is remarkable to think that the air we breathe today is the result of billions of years of transformation. The earliest atmosphere, thick with steam and volcanic gases, would eventually be altered by geological processes and later by life itself. Photosynthetic organisms, once they appeared, would begin releasing oxygen, slowly changing the composition of the air over hundreds of millions of years. But at this stage, the atmosphere was still in its earliest form, shaped almost entirely by geology rather than biology. The interaction between atmosphere, crust, and ocean was already beginning to influence the planet in important ways. Rainwater reacted with volcanic rock, breaking down minerals and carrying them into the growing oceans. Carbon dioxide dissolved in water and reacted with minerals, gradually removing some of it from the atmosphere and storing it in rocks. These processes help regulate the planet's climate, preventing temperatures from rising too high despite the greenhouse gases present. In a sense, the Earth was beginning to develop the complex feedback systems that still help stabilize its environment today. Above all, the atmosphere was part of a larger system, one that included the cooling crust, the forming oceans, and the heat still rising from the interior. None of these components acted independently. Changes in one influenced the others, creating a dynamic, evolving world. The skies of steam and ash would not last forever. Over millions of years, as oceans deepened and volcanic activity gradually declined, the atmosphere would begin to clear. Clouds would thin, and the sky would slowly take on the appearance we recognize today. Yet during this early period, the thick atmosphere played a crucial role. It trapped heat, allowed water to cycle between surface and sky, and provided the conditions necessary for the next stage in Earth's history. Imagine a planet where the sound of rain never stops. Not for an afternoon, not for a season, but for spans of time so long that any familiar sense of weather would lose its meaning. The clouds above the young Earth were thick, towering and restless, and the atmosphere held vast quantities of water vapour released from volcanoes and delivered by icy bodies from space. As the surface slowly cooled, that vapour began to condense, and once the process truly began, it continued on a scale almost impossible to picture. This was the beginning of the first oceans, and it did not happen quickly. To understand why rain could last for such immense periods, it helps to think about how much water was present in the early atmosphere. During the era when the Earth was still largely molten, enormous amounts of steam had accumulated in the air. Volcanoes released water trapped in minerals deep within the mantle, and each eruption added more vapour to the sky. At the same time, comets and water-rich asteroids striking the planet contributed additional water, much of which was instantly vaporized by the heat of impact and mixed into the atmosphere. For a long time, the surface remained too hot for liquid water to remain stable. Rain would fall only to boil away again, rising back into the sky in great columns of steam. But as millions of years passed, the balance slowly shifted. Cooling outpaced heating in more regions, the crust thickened, temperatures dropped just enough that some of the falling water began to remain on the surface instead of vanishing immediately. At first, this may have happened only in isolated basins, shallow depressions where water could collect temporarily. Pools formed, lingered, and sometimes evaporated again. Yet each cycle of evaporation carried heat upward and away, helping the planet cool further. Over immense stretches of time, the process reinforced itself. More cooling allowed more water to remain, and more water remaining allowed further cooling. Eventually, rainfall became persistent on a global scale. It is difficult to imagine what such rainfall would have been like. Storm systems may have covered enormous areas, with clouds rising high into the atmosphere and releasing continuous downpours. Thunder and lightning were likely common, driven by intense convection and volcanic plumes. Rivers, if they existed at this stage, would not have looked like the winding waterways we know today. Instead, sheets of water may have flowed across broad expanses of bare rock, carving channels that were quickly reshaped by new lava flows or impacts. As water accumulated, the first true oceans began to form. These early oceans were very different from the ones we know now. They were probably warmer, perhaps even hot in some regions, heated from below by volcanic activity, and from above by a thick greenhouse atmosphere. They contained large amounts of dissolved minerals washed from newly formed crust by constant rain. The chemistry of seawater was still evolving, shaped by reactions between water, rock, and gases in the atmosphere. The colour of these early oceans is uncertain, but they may not have been the deep blue we associate with modern seas. Suspended particles, dissolved iron, and volcanic sediments could have given the water a darker or greenish tint. Sunlight reaching the surface would have been filtered through thick clouds, producing a dim, diffuse illumination rather than the bright sparkle of modern waves. Meanwhile, the seafloor itself was not stable. Heat from the interior drove vigorous volcanic activity beneath the water. Cracks in the crust allowed seawater to circulate downward, where it was heated and then forced back upward, carrying dissolved minerals with it. These early hydrothermal systems were widespread, releasing heat and chemicals into the oceans and creating environments that would later become important in the story of life. But during this time, life had not yet appeared, at least as far as current evidence suggests. The oceans were a setting being prepared, shaped by geology and chemistry, waiting for processes that would take hundreds of millions of years more to unfold. Rain continued to fall. One reason the rainfall persisted so long is that the atmosphere contained far more water vapour than today. The modern water cycle, in which oceans evaporate, form clouds and produce rain, was only just beginning to establish itself. In those early ages, the atmosphere was still adjusting, gradually losing excess vapour as it condensed and accumulated on the surface. This process may have lasted millions of years. It was not a single storm or even a series of storms, but a prolonged period in which precipitation dominated the planet's climate. Low-lying regions filled first, forming shallow seas that gradually deepened as more water arrived. The formation of oceans also began to influence the atmosphere in return. Water is an excellent absorber of carbon dioxide, and as the oceans expanded, they began removing some of this gas from the air. Carbon dioxide dissolved in seawater reacted with minerals and was eventually locked into rocks, a process that helped regulate the planet's temperature. Without this natural regulation, the greenhouse effect might have remained so strong that the surface would have stayed too hot for stable oceans to exist. Instead, the interaction between ocean, atmosphere, and crust gradually brought the climate into a more moderate range. It is interesting to consider how quiet parts of the planet may have become once large oceans formed. The constant impacts of earlier ages had declined, and in regions far from active volcanoes, the dominant sound might have been the steady fall of rain and the movement of waves along newly formed shorelines. Shorelines themselves would have been different from those we know. There were no beaches of sand yet because sand requires long periods of weathering and erosion. Instead, the edges of early oceans may have been lined with dark volcanic rock, fractured and uneven, with water pooling in cracks and channels. Tides, influenced by the moon, were stronger than they are today because the moon was closer to Earth. These tides may have risen and fallen over broad, shallow coastal areas, repeatedly flooding and exposing surfaces. Such environments, where water and minerals interacted under changing conditions, would later become important settings for complex chemistry. Another detail often overlooked is the role of time in smoothing the landscape. Rain and flowing water began wearing down sharp volcanic surfaces, carrying sediments into basins. The earlier sediments accumulated on the ocean floor, forming layers that would one day become some of the oldest surviving rocks on Earth. Even the composition of the atmosphere began to change as oceans expanded. Water vapour decreased as more of it condensed and remained on the surface. Clouds gradually became less dominated by steam and more by liquid droplets. Over immense spans of time, the sky itself began to change in appearance. Yet the planet was still far from calm. Volcanoes continued to erupt, releasing new gases and heat. Occasional impacts still occurred, sometimes large enough to create temporary disturbances in the oceans and atmosphere. The Earth was entering a more stable phase, but stability was relative. Change was still constant. just slower and less catastrophic than before. Scientists today study ancient minerals, particularly tiny crystals of zircon, to learn about this period. Some of these crystals, more than 4 billion years old, contain chemical signatures suggesting that liquid water existed on the surface at that time. These small, durable minerals are among the few surviving witnesses to the birth of the oceans, carrying within them traces of conditions that existed when the Earth was still very young. From these clues, researchers have concluded that oceans may have formed earlier than once believed, perhaps within a few 100 million years of the planet's formation. That may sound like a long time, but in geological terms it is surprisingly fast. The presence of oceans had profound consequences. Water is not only a solvent but also a medium in which chemical reactions can occur more easily. Molecules can move, collide, and combine in ways that are difficult in dry environments. The oceans became vast laboratories of chemistry, containing dissolved minerals, organic molecules delivered by meteorites, and energy from heat and sunlight. No one knows exactly how life began, but many scientists believe that the earliest steps took place in water, perhaps near hydrothermal vents, or in shallow tidal regions where conditions changed regularly. The formation of stable oceans made such environments possible. It is remarkable to think that every drop of water in today's seas has been part of this long cycle, evaporating, condensing, freezing, melting, circulating through rocks and living organisms, and returning again to the oceans. The water falling as rain in those early ages is, in a sense, still here, part of an unbroken history stretching back billions of years. As rainfall gradually decreased and oceans deepened, the planet's appearance continued to change. From space, the Earth would no longer have looked like a glowing volcanic world shrouded in steam. Instead, dark expanses of water began to dominate the surface, broken by patches of newly formed crust and islands of volcanic rock. Clouds still covered much of the sky, and storms were still frequent, but the atmosphere was slowly becoming clearer. The balance between evaporation and precipitation was approaching something closer to the modern water cycle, though temperatures remained higher and the chemistry of the oceans was still evolving. These changes unfolded so slowly that no single moment marked the completion of the oceans. There was no day when the last raindrop fell and the seas were suddenly full. Instead, the process was gradual, almost imperceptible, the result of countless storms, countless cycles of evaporation and condensation, and the steady cooling of a once molten world. For hundreds of millions of years after the first oceans began to spread across the cooling surface, the Earth remained completely without life. There were seas, clouds, storms, volcanic islands, and an atmosphere slowly changing in composition. But nothing swam, nothing grew, and nothing breathed. The planet was active in every geological sense, yet biologically it was silent. It can be difficult to picture a world like that, because every landscape we know today, from the deepest ocean trench to the highest mountain slope, contains living organisms of some kind. Even the most extreme environments on modern Earth, boiling hot springs, frozen deserts, and deep underground rock layers, contain microbes. Life has become so widespread that it feels almost inseparable from the planet itself. But in those early ages, life had not yet begun, and the Earth functioned entirely through physical and chemical processes. The oceans, though vast, were empty of fish, algae, or bacteria. Their waters moved under the influence of wind, tides, and volcanic heat alone. Waves broke against rocky shores that had never known the grip of roots or the burrowing of animals. The seafloor, though active with volcanic vents and circulating currents, contained only minerals, dissolved chemicals, and heat rising from the interior. The atmosphere above was also very different from what we know today. Oxygen was almost entirely absent, and without oxygen there was no ozone layer to block much of the sun's ultraviolet radiation. High-energy light reached the surface and upper layers of the ocean more easily, breaking apart molecules and driving chemical reactions that would be impossible under modern conditions. Lightning was frequent, especially in regions where warm, moist air rose rapidly above volcanic landscapes or warm oceans. Each lightning strike delivered a brief but powerful burst of energy into the atmosphere, breaking molecular bonds and allowing new combinations of atoms to form. Carbon dioxide, methane, nitrogen and water vapour interacted under these conditions, producing a variety of organic molecules, simple carbon-based compounds that would later play an important role in the development of life. At the time, however, these molecules were simply part of the chemistry of the planet. There was no metabolism, no reproduction, no cells, only reactions driven by heat, light, and electrical energy. It is interesting to consider how much chemistry was already underway in those oceans. Water is an effective solvent, meaning it allows many substances to dissolve and move freely. Minerals eroded from volcanic rock entered the oceans, bringing elements such as iron, magnesium, phosphorus and sulfur into solution. Hydrothermal vents on the seafloor released additional chemicals, including hydrogen and various metal ions, into the surrounding water. Near these vents, seawater circulated through cracks in the crust, heated by magma below, and returned to the ocean carrying dissolved minerals. These environments were rich in chemical gradients, differences in temperature, pressure, and composition that could drive reactions. Even without life, these systems were dynamic, constantly mixing and transforming materials. The oceans themselves were probably warmer than modern seas, perhaps significantly so in some regions. Heat from the planet's interior combined with a greenhouse atmosphere kept temperatures elevated. Yet conditions were not uniform. Some areas were cooler, others hotter depending on volcanic activity, ocean circulation, and depth. Sunlight penetrated the upper layers of the water, though perhaps not as deeply as it does today, if suspended particles and dissolved iron were abundant. In shallow coastal areas, cycles of evaporation and flooding occurred as tides rose and fell under the strong gravitational influence of the moon, which was still closer to Earth than it is now. These tidal zones may have been especially important for chemistry. When water evaporates, dissolved substances become more concentrated, making reactions more likely. When fresh water returns with the next tide, it dilutes and redistributes those substances, allowing new interactions to occur. Repeated over long periods, these cycles created environments where complex molecules could gradually form. Still, it is important to remember that this was not a sudden or directed process. There was no plan guiding these reactions, no inevitable path leading quickly toward life. Chemistry simply unfolded according to the laws of physics, producing countless combinations of molecules, most of which were unstable or short-lived. Time, once again, was the key factor. Over millions of years, reactions repeated, products accumulated, and more complex compounds occasionally formed. Some molecules proved more stable than others and persisted longer in the environment. Others broke apart quickly and disappeared. Meanwhile, the surface of the Earth continued to change. Volcanoes erupted frequently, building new landforms and releasing gases into the atmosphere. The crust shifted and fractured under the influence of internal heat. Meteorites and smaller asteroids still struck the planet from time to time, delivering additional materials from space, including organic compounds that had formed in the cold regions of the solar system. These impacts were less frequent than in earlier eras, but still significant. Some may have temporarily heated large regions of ocean or atmosphere, altering local conditions and driving further chemical reactions. Night on this lifeless world would have been very dark in places far from volcanic activity. Without artificial lights or bioluminescent organisms, the only natural illumination came from the moon, stars, and occasional lightning. The moon itself, larger in the sky than today, cast brighter tides and stronger reflections across the ocean surface. Yet even in this darkness, chemistry continued. Many reactions do not depend on sunlight but on heat, or the presence of reactive minerals. Deep in the oceans, far beyond the reach of light, hydrothermal systems provided energy and chemical gradients that could support complex interactions. Some scientists believe that environments like these may have been among the most likely places for life to begin. The constant flow of chemicals, combined with stable temperatures and protection from ultraviolet radiation, created conditions favourable for the formation of increasingly complex molecules. One of the most important steps in the origin of life was the formation of molecules capable of storing information and replicating themselves, such as RNA or related compounds. Exactly how and where this happened remains uncertain, but it likely required long periods of gradual chemical evolution with many intermediate stages. It is worth pausing to reflect on how slow this process may have been. From the formation of the first oceans to the earliest evidence of life, hundreds of millions of years may have passed. That is a span of time far longer than the entire history of animals on Earth. During those ages, the planet remained silent in the biological sense, but not inactive. Winds moved across the oceans, storms formed and dissipated, continents, still small and fragmented, shifted slowly. Chemical reactions continued in water, in rock, and in the atmosphere. The absence of life also meant that many processes we take for granted today did not yet exist. There was no photosynthesis producing oxygen, no plants stabilizing soils, no microbes breaking down organic material. The composition of the atmosphere was controlled almost entirely by volcanic activity, weathering of rocks, and chemical interactions with the oceans. Iron dissolved in seawater, giving the oceans a different chemistry from today. Without oxygen, iron remained in soluble form rather than precipitating out as rust-coloured sediments. This would later change dramatically once photosynthetic organisms began releasing oxygen into the environment, but that transformation still lay far in the future. Another difference was the soundscape of the planet. Today, even remote environments are filled with subtle sounds, wind moving through vegetation, insects, birds and waves interacting with living shorelines. On the early Earth, the sounds would have been limited to wind, water, thunder, and volcanic activity. Shores were bare rock. Oceans were empty of swimmers. The only movement came from physical forces. And yet, despite this apparent emptiness, the conditions necessary for life were slowly coming together. Organic molecules formed in the atmosphere and oceans. Minerals provided surfaces where reactions could occur more easily. Energy from sunlight, lightning, and geothermal heat drove processes forward. At some point, perhaps in many places independently, certain chemical systems became capable of self-replication, the ability to make copies of themselves. Once that threshold was crossed, even in the simplest form, the world changed in a profound way, because natural selection could begin to operate. Molecules that replicated more efficiently became more common. Systems that were more stable persisted longer. But before that turning point, there was a long era in which chemistry alone shaped the planet, setting the stage but not yet producing life. It is remarkable to think that the rocks beneath our feet and the water in the oceans have existed through both of these worlds, the lifeless earth of chemistry alone and the living earth that followed. The transition between them was gradual, unfolding over immense spans of time, and many details remain uncertain, preserved only in faint traces within ancient rocks. Even as these chemical processes continued, the planet itself was still subject to forces from beyond. The solar system had not yet fully settled. Large impacts, though less frequent than before, were still possible, and some of them were powerful enough to reshape entire regions of the surface or temporarily alter the atmosphere and oceans. Several 100 million years had already passed since the Earth first formed, and by this stage oceans existed, a crust had begun to stabilize in places, and the atmosphere, though still very different from today's, had settled into a more persistent form. If someone could have observed the planet from afar during these ages, they might have seen a world that appeared calmer than before, less dominated by glowing magma and constant collisions. Yet this calm was temporary. A new period of violence was approaching, one that would once again reshape the surface and remind the young planet that the solar system was still an unsettled place. Scientists now call this interval the Late Heavy Bombardment, a time when large numbers of asteroids and other rocky bodies struck the inner planets. The phrase may sound dramatic, but it reflects a real and measurable event recorded most clearly on the surface of the Moon. The Moon, lacking atmosphere, weather or active geology, preserves ancient impact scars far better than Earth does. When we examine its surface, especially the heavily cratered highlands, we see evidence of a period when impacts were far more frequent than at any time since. Those same impacts must also have struck the Earth, although most traces of them have been erased by erosion, tectonic activity, and the constant recycling of crust. To understand why this bombardment happened, it helps to look outward, far beyond the Earth itself, to the giant planets. Jupiter, Saturn, Uranus, and Neptune did not always occupy the exact orbits we see today. Early in the solar system's history, their positions were slightly different, and over time gravitational interactions between them caused slow but significant shifts. As these massive planets moved, they disturbed vast populations of smaller objects, particularly those in regions now known as the asteroid belt and the outer reservoirs of icy bodies. Many of these disturbed objects were thrown onto new paths, some of which crossed the orbits of the inner planets. This process did not happen all at once. It unfolded over millions of years, gradually sending waves of debris inward toward Mercury, Venus, Earth, and Mars. The inner solar system, which had been growing quieter after the earlier stages of planet formation, suddenly became dangerous again. From the perspective of the Earth's surface, the sky would have changed in subtle but unsettling ways. Meteors, already more common than they are today, became even more frequent. Some burned up in the atmosphere, producing streaks of light. Others reached the surface, sometimes with explosive force. Occasionally, much larger bodies struck, releasing energy equivalent to millions of modern nuclear weapons. These impacts could excavate enormous craters, vaporize rock, and send debris high into the atmosphere or even into orbit. It is difficult to imagine the scale of such events. One large asteroid impact can release more energy than all the volcanic eruptions on Earth, combined over many centuries. The heat generated can ignite global wildfires on a modern Earth, but in the ancient world, where vegetation did not yet exist, the primary effects would have been shock waves, intense heating, and massive disturbances to the oceans and atmosphere. When a large impact struck the ocean, it would have produced enormous waves, far larger than any tsunami in recorded history. These waves would have travelled across entire ocean basins, crashing against rocky shores and reshaping coastlines that were still young and unstable. At the same time, impacts threw vast amounts of dust and vaporized rock into the atmosphere. These particles could block sunlight for months or years, temporarily cooling the surface. Later, as the dust settled and greenhouse gases released by impacts accumulated, temperatures might have risen again. So the climate during this period may have fluctuated dramatically, with alternating intervals of cooling and warming driven by impacts of varying sizes. The late heavy bombardment was not a single moment, but an extended period, possibly lasting several 100 million years. During this time, the Earth endured repeated impacts, some small, some enormous. Each one altered the surface in some way, excavating basins, redistributing materials, and sometimes melting large regions of crust. Yet even these destructive events played a role in shaping the planet's future. Impacts delivered new minerals and elements from space, including metals and volatile compounds. Some scientists believe that a portion of Earth's water and organic molecules may have been delivered during this period, carried by asteroids and comets from colder regions of the solar system. This idea is supported by the composition of certain meteorites, which contain complex organic molecules formed in space long before the Earth existed. When such bodies struck the planet, they brought these materials with them, adding to the chemical diversity of the oceans. It is interesting to consider how resilient the young Earth was during this time. Oceans, though occasionally disturbed by impacts, persisted. The atmosphere, though repeatedly altered, remained thick enough to retain heat and water. Chemical processes in the oceans continued, even as the surface experienced periodic upheavals. In this sense, the Earth was gradually becoming more stable, not because impacts had ceased, but because the planet had grown large enough and developed systems robust enough to absorb disturbances without losing its essential structure. Meanwhile, the Moon was also being struck. Many of the large basins visible on its surface today, such as Mare Imbrium and Mare Serenitatis, formed during this period. These basins are so large that they can be seen with the naked eye as the dark regions of the Moon's face. When these impacts occurred, they must have been visible from Earth as brilliant flashes of light, brief but intense, marking the formation of craters hundreds of kilometers wide. Because the Moon has no atmosphere, impacts there were even more dramatic in appearance than on Earth. Debris thrown upward would have arced in long, graceful trajectories before falling back, and the scars of those events remain preserved to this day. On Earth, by contrast, erosion and tectonics have erased most direct evidence. Only a few ancient impact structures remain, and many of those are deeply buried or heavily altered. The geological record of this era is fragmentary, reconstructed from indirect clues rather than preserved landscapes. Despite this, the overall pattern is clear. The inner solar system experienced a surge in impacts, followed by a gradual decline as the supply of wandering bodies was depleted or their orbits stabilized. As millions of years passed, the rate of impact slowly decreased again. The skies, once filled with falling worlds, grew quieter. Large collisions became less frequent, and the intervals between them lengthened. This gradual decline marked an important turning point. With fewer catastrophic disturbances, the Earth's surface could stabilize for longer periods. Oceans deepened and became more persistent. The atmosphere continued evolving, influenced by interactions with water and rock. Chemical processes in the oceans, uninterrupted for longer stretches of time, became increasingly complex. Organic molecules accumulated in certain environments, particularly near hydrothermal vents and in shallow coastal regions where tides and evaporation concentrated dissolved substances. The late heavy bombardment, though destructive, may therefore have played a paradoxical role. By delivering new materials and stirring the oceans and crust, it may have contributed to the chemical diversity necessary for life to arise, even as it repeatedly disrupted the surface. There is something quietly remarkable about that balance. A planet must be active enough to mix materials and create chemical opportunities, yet stable enough to allow those processes to continue without being completely reset by constant catastrophe. The Earth, by chance or by the natural consequences of its size and position, passed through that narrow window. Night after night, year after year, the frequency of visible impact gradually declined. The Moon, still closer than today, continued to raise strong tides in the oceans, and the interaction between ocean, atmosphere, and crust became more intricate. Volcanic activity remained widespread, releasing gases and heat from the interior. The crust continued to move and reshape itself under the influence of mantle convection. But the most violent era of falling worlds was coming to an end. It is difficult to imagine how different the sky must have seemed once that change became noticeable. Generations of storms and occasional impacts gave way to longer intervals of quiet, where the dominant sounds were wind, waves, and distant eruptions rather than the explosive arrival of objects from space. The solar system itself was settling into the more stable configuration we recognize today. The giant planets had largely reached their present orbits. The asteroid belt, though still populated, contained far fewer objects on trajectories that crossed Earth's path. The supply of large impactors had diminished. With that decline, the Earth entered a new phase in its history, one in which the surface, atmosphere and oceans could evolve under more stable conditions for extended periods. Deep beneath the surface of the early Earth, far below the cooling crust and the growing oceans, enormous movements were taking place that no eye could have seen. The ground, which from above might have appeared solid and slowly stabilizing, was resting on layers of rock that were still intensely hot, slowly flowing and constantly in motion. The young planet was not quiet inside. It was restless, driven by heat left over from its formation and by the decay of radioactive elements buried deep within its interior. That internal heat shaped nearly everything about the early Earth. Powered volcanoes cracked the crust, built new seafloor and helped recycle the outer layers of the planet again and again. Even today, billions of years later, much of Earth's geology is driven by heat rising from within, but in those early ages the process was stronger, faster and far more dramatic. To understand why, it helps to consider where that heat came from. Part of it was inherited from the violent beginnings of the planet. Every collision that built the Earth released enormous energy, and much of that energy remained trapped inside. Another portion came from differentiation, the sinking of heavy elements like iron toward the core, which released heat through friction and compression. And then there was radioactive decay, a process in which unstable atoms slowly release energy over time. In the early Earth, radioactive elements were more abundant than they are now, meaning that this internal heating was even more significant. All of this combined to keep the mantle, the thick layer of rock between the crust and the core, hot enough to flow, not like water or lava at the surface, but slowly, over thousands or millions of years, in vast circulating currents. These currents are called convection currents, and they are one of the most important forces shaping a rocky planet. When rock deep within the mantle heats up, it becomes slightly less dense and begins to rise. As it approaches the cooler regions near the crust, it loses heat, becomes denser, and slowly sinks again. This cycle repeats continuously, creating immense, slow-moving currents that push and pull on the crust above. In the early Earth, these currents were more vigorous than they are today because the temperature differences were greater and the overall heat content of the planet was higher. The crust above was thinner and weaker, making it easier for these internal forces to break through. As a result, volcanoes were far more common. Instead of isolated volcanic peaks separated by long distances, entire regions of the surface may have been dotted with eruptions. Lava flowed frequently, sometimes covering vast areas before cooling. Gases poured into the atmosphere in enormous quantities, reinforcing the thick, hazy skies that still covered much of the planet. It is interesting to think about how these early eruptions differed from the volcanic events we know today. Modern volcanoes often build steep cones because lava tends to erupt from relatively localized vents. On the early Earth, with a thinner crust and higher internal heat, eruptions may have been more widespread, forming broad lava plains rather than towering peaks. These lava plains, once cooled, formed a new crust. But the story did not end there, because the same forces that created the crust were also working to reshape it. Rising mantle currents pushed upward, stretching and cracking the surface. In other places, denser crust began to sink back into the mantle, melting and recycling its material. This process, in its earliest form, marked the beginnings of tectonic activity. Plate tectonics, as it operates today, involves large, rigid plates moving slowly across the surface, colliding, separating, and sliding past one another. In the early Earth, the process was probably less organized. The crust may have been broken into many smaller fragments, shifting and interacting in complex ways. Some researchers believe that the first true plate tectonics began during this time, while others suggest that the process developed gradually over hundreds of millions of years. Whatever the exact mechanism, the surface of the planet was not fixed. Land masses formed and broke apart. New crust formed at volcanic ridges and was destroyed in regions where it sank back into the mantle. Over immense spans of time, this recycling helped regulate the planet's temperature and chemical composition. Volcanoes also played another important role. They continued releasing gases that shaped the atmosphere. Carbon dioxide, water vapour and nitrogen escaped from the interior, replenishing the atmosphere even as chemical reactions and ocean processes removed some of these gases. Without this continuous supply, the atmosphere might have thinned too quickly, and the planet's climate might have changed in ways that made stable oceans difficult to maintain. The oceans themselves were influenced by this internal heat. In many places, seawater seeped into cracks in the crust and travelled downward, heated by magma, and then returned to the ocean through hydrothermal vents. These vents released hot, mineral-rich water into the surrounding sea, creating environments where temperatures and chemistry differed sharply from the surrounding water. Today, such vents support rich ecosystems of organisms that thrive without sunlight, but in the early Earth they were purely chemical environments, places where heat and dissolved minerals interacted in complex ways. These environments would later become important in theories about the origin of life, but at the time they were simply part of the planet's natural circulation of heat and matter. Another effect of the Earth's internal heat was the gradual formation of continents. The earliest crust was mostly basaltic, similar to the rock that forms modern ocean floors. Over time, repeated cycles of melting and recycling produced lighter, silica-rich rocks that were less dense and more buoyant. These rocks began to accumulate in certain regions, forming the first stable continental nuclei. These early land masses were small compared to modern continents, and they were constantly reshaped by volcanic activity and tectonic forces. Still, they represented the beginnings of something new, areas of thicker, more stable crust that would persist and grow over billions of years. Weathering began to act on these early continents as well. Rain falling on exposed rock dissolved minerals and carried them into rivers and oceans. Sediments accumulated in shallow basins, forming layers that would eventually harden into sedimentary rock. These processes, familiar to us today, were already underway, though the landscapes in which they occurred were still very different from those of the modern world. Meanwhile, the interior of the planet continued to evolve. The core, composed mostly of iron and nickel, remained extremely hot and partly liquid. Movements in the outer core generated a magnetic field, which extended outward into space, forming a protective shield around the planet. This magnetic field played a crucial role in preserving the atmosphere. The solar wind, a stream of charged particles flowing outward from the sun, can gradually strip away a planet's atmosphere if no magnetic field is present. Mars, for example, lost much of its atmosphere after its internal dynamo weakened. Earth's strong magnetic field helped prevent such losses, allowing the atmosphere to remain thick and stable. It is remarkable to think that the invisible movements of molten metal, thousands of kilometers beneath the surface, were helping protect the oceans and skies above. The surface, however, was still far from calm. Earthquakes were likely frequent, driven by shifting crust and rising magma. Volcanic eruptions could last for decades or centuries, building new land and reshaping coastlines. Ash and gases released into the atmosphere sometimes altered the climate temporarily, cooling the surface by blocking sunlight or warming it by adding greenhouse gases. Even the shape of the oceans was influenced by tectonics. As new crust formed and old crust sank, ocean basins changed depth and extent. Sea levels rose and fell over long periods, flooding some regions and exposing others. All of these processes unfolded slowly by human standards but rapidly in geological terms. Millions of years passed, and the planet continued to change, its surface shaped by the interplay of internal heat and external forces. It is easy to think of the Earth as solid and unchanging beneath our feet, but in reality the ground we stand on is part of a system that is still moving, still reshaping itself, still driven by heat that has been trapped inside since the planet's earliest days. Back then that restlessness was even more pronounced. The crust was thinner, the mantle hotter, and the forces at work more intense. The planet was young, still settling into the balance that would allow long-term stability. And yet, despite the constant motion, a new kind of balance was emerging. Oceans had formed and persisted. The atmosphere, though still lacking oxygen, had stabilized in composition. Chemical processes in water and rock were becoming more complex. Above, the sun continued to shine, though it was still slightly dimmer than it is today. This presents an interesting puzzle that scientists have studied for decades. If the young sun was fainter, how did the Earth remain warm enough for liquid water to exist? Long before the sunlight that warms the Earth today reached its present strength, the young sun shone with noticeably less energy. It was not dim in any everyday sense. If you could have stood on the early Earth and looked upward through breaks in the thick clouds, the sun would still have appeared bright enough to light the surface and cast shadows. Yet compared to its current output, it produced significantly less heat, perhaps only about 70% of what it gives off now. At first glance, that creates a puzzle. A weaker sun should have meant a colder Earth. With less incoming energy, the ocean should have frozen, or at least remained locked beneath thick layers of ice. Yet geological evidence tells a different story. Ancient minerals and rock formations indicate that liquid water existed on the surface for vast spans of time during these early ages. Oceans were present, and they were not frozen solid. So how did a planet orbiting a fainter sun remain warm enough to sustain liquid water? This question has intrigued scientists for decades, and is often called the faint young sun paradox. The word paradox here does not mean an unsolvable contradiction, but rather a situation where the initial expectation does not match what actually happened. Solving this puzzle requires looking not just at the sun, but at the atmosphere, the oceans, and the internal workings of the planet itself. One of the most important factors was the composition of the early atmosphere. Unlike the modern atmosphere, which contains significant oxygen and relatively modest amounts of carbon dioxide, the air of the early Earth was rich in greenhouse gases. Carbon dioxide, methane, and water vapour were all present in far higher concentrations than they are today. Greenhouse gases have a particular property that makes them important for planetary climates. They allow sunlight, which arrives mostly as visible light, to pass through the atmosphere and warm the surface. But when the surface radiates heat back upward in the form of infrared radiation, greenhouse gases absorb some of that heat and re-radiate it in all directions, including back toward the ground. This process slows the loss of heat into space and keeps the planet warmer than it would otherwise be. Without greenhouse gases, the average temperature of the Earth today would be well below freezing. In the distant past, when the sun was weaker, the presence of larger amounts of these gases was even more crucial. Volcanoes were the primary source of carbon dioxide during this time. Each eruption released gases trapped in the mantle, gradually building a thick atmosphere capable of trapping heat efficiently. Methane may also have been present in significant quantities, produced by chemical reactions in the oceans and crust, or possibly by early microbial life later in this era, though that stage lies somewhat ahead in the story. Water vapour itself is also a powerful greenhouse gas. The early Earth's atmosphere, still rich in steam from widespread volcanism and warm oceans, would have retained heat effectively. The combined effect of these gases created a climate that remained warm enough for liquid water, even under a fainter sun. Another factor that influenced the planet's temperature was the arrangement of land and sea. Early continents were smaller, and much of the surface was covered by oceans. Water absorbs and stores heat more effectively than bare rock, moderating temperature changes between day and night and between seasons. This buffering effect may have helped keep the climate relatively stable. Clouds also played a role, though their exact influence is complex. Clouds can both cool and warm a planet. They reflect sunlight back into space, reducing heating, but they also trap infrared radiation, contributing to warming. The balance between these effects depends on the thickness, altitude, and composition of the clouds. In the early Earth's atmosphere, clouds were probably widespread and varied, and their overall impact likely changed over time. There is also evidence that the rotation of the Earth was faster in those early ages, meaning shorter days and nights. Faster rotation influences atmospheric circulation, wind patterns and ocean currents, which in turn affect how heat is distributed around the planet. While this factor alone would not solve the faint sun puzzle, it may have contributed to a more even distribution of warmth. Another important process involved the interaction between the atmosphere and the crust. Carbon dioxide released by volcanoes did not remain in the air indefinitely. Rainwater dissolved some of it, forming weak carbonic acid that reacted with rocks. These reactions gradually removed carbon dioxide from the atmosphere and locked it into minerals, a process known as chemical weathering. This weathering process acts as a natural thermostat over long periods. When temperatures rise, weathering accelerates, removing more carbon dioxide and cooling the planet. When temperatures fall, weathering slows, allowing carbon dioxide to accumulate and warm the planet again. This feedback mechanism helps regulate climate over millions of years. On the early Earth, this system was already beginning to operate, though perhaps less efficiently than it does today. Even so, it contributed to maintaining temperatures within a range where liquid water could persist. The oceans themselves also influence climate in subtle ways. Dissolved minerals affected the chemistry of seawater, which in turn influenced how carbon dioxide was absorbed and stored. Hydrothermal vents on the seafloor released heat and chemicals, adding further complexity to the interactions between ocean and atmosphere. All of these processes work together, not in perfect balance at every moment, but in a long-term interplay that allowed the planet to remain warm enough despite the faint young sun. It is interesting to think about how the sky might have appeared during this time. The sun, though slightly dimmer, would still have been bright enough to dominate the daylight hours. However, the atmosphere, thicker and richer in greenhouse gases, may have scattered light differently, giving the sky a somewhat different colour or quality. Haze and clouds were likely more common, and clear blue skies may have been rare. At night the moon would still have appeared larger than it does today, though it was slowly receding from Earth's orbit. Tides were stronger, shaping coastlines and stirring shallow seas. Stars would have shone clearly on nights when clouds parted, and meteors, though less frequent than in earlier ages, still appeared from time to time as remnants of the solar system's formation crossed Earth's path. Temperature across the planet was probably not uniform. Regions near active volcanic zones may have been warmer, while others were cooler. The poles, if they existed in a form similar to today's, may have been colder, though evidence suggests that widespread global glaciation did not dominate this era. There may have been intervals when parts of the planet cooled significantly, perhaps even forming regional ice, followed by warmer periods when greenhouse gases increased again. Climate has never been perfectly stable, and even in these early ages fluctuations likely occurred over tens or hundreds of thousands of years. One of the remarkable aspects of this period is how resilient the Earth proved to be. Despite a weaker sun, despite occasional large impacts, despite intense volcanic activity, the planet maintained oceans and an atmosphere capable of supporting complex chemistry. Conditions were not gentle, but they were stable enough over long spans of time for gradual changes to accumulate. That stability, relative though it was, mattered greatly. Chemistry requires time. Molecules must form, interact, break apart, and recombine countless times before more complex structures emerge. If the environment changes too violently or too frequently, these processes cannot proceed far. By this stage, the Earth had reached a point where long intervals passed without catastrophic disruptions. Oceans persisted. Temperatures remained within a range that allowed water to remain liquid. Chemical reactions in the oceans and along coastlines continued, slowly increasing in complexity. It is also worth remembering that the sun itself was changing during this time. Stars like the sun grow gradually brighter as they age, because the fusion of hydrogen into helium in their cores changes their internal structure. Over billions of years, the sun's luminosity has increased steadily. The faint young sun of the distant past would slowly become the brighter sun of later ages. This gradual brightening meant that the balance between greenhouse gases and solar radiation was not fixed. The atmosphere and oceans continued to adjust, removing or adding carbon dioxide as conditions changed. The planet's climate evolved in response, maintaining a delicate equilibrium. Another detail that sometimes surprises people is that a slightly dimmer sun would have produced less ultraviolet radiation in some wavelengths, but still enough to drive important chemical reactions in the atmosphere and upper oceans. Ultraviolet light can break apart molecules and create reactive fragments that recombine into new compounds. These reactions played a role in producing organic molecules, some of which accumulated in the oceans. Lightning, volcanic heat, and hydrothermal activity provided additional energy sources. Together, these processes created an environment rich in chemical possibilities. No one knows exactly how long it took for the first self-replicating systems to emerge, but by this time, many of the necessary ingredients were present: liquid water, a variety of organic molecules, sources of energy, and stable environments where reactions could proceed over long periods. The faint young sun paradox, once puzzling, now appears as a reminder of how interconnected planetary systems are. The brightness of a star, the composition of an atmosphere, the chemistry of oceans, and the movement of a planet's interior all influence one another. A change in any one of these factors can alter the entire system. In the case of the early Earth, these factors combined in a way that allowed the planet to remain warm enough for liquid water and complex chemistry, even under a weaker sun. It was not a perfect or unchanging climate, but it was suitable for the slow processes that would eventually lead to something entirely new. By the time the oceans had settled into long-lasting basins and the atmosphere had begun to stabilize, the Earth had become a place where complex chemistry could unfold over very long stretches of time. There were still volcanoes, still storms, still shifting crust and occasional impacts, but the intervals between major disruptions were now long enough for slow processes to build upon one another. And it was during these immense spans of quiet change that something subtle, yet profoundly important, began to take shape. At first, nothing about it would have seemed remarkable. There were no sudden flashes of light, no dramatic transformation visible from the sky. The ocean still moved as they always had, tides rising and falling under the pull of the moon, rain falling and evaporating, minerals dissolving and settling again. But within the water, among dissolved chemicals and along the surfaces of rocks and minerals, molecules were beginning to arrange themselves in new and increasingly complicated ways. To understand how this happened, it helps to consider what makes life different from non-living chemistry. Living systems are built from molecules that can store information, replicate, and carry out reactions that sustain themselves. None of these properties appear instantly. They arise gradually from simpler chemical interactions, and the early Earth provided an environment where such interactions could occur repeatedly, over millions of years. The oceans were central to this process. Water does more than simply dissolve substances. It allows molecules to move freely, to collide, to react. In a dry environment, atoms and molecules are often locked in place, unable to rearrange easily. In water, they are constantly in motion, and this motion increases the chances that new combinations will form. The early oceans were rich in dissolved minerals. Iron, magnesium, calcium, phosphorus, sulfur, and many other elements had been washed from the crust by rain or released from hydrothermal vents. Carbon compounds, formed in the atmosphere or delivered by meteorites, were also present. Energy from sunlight, lightning, and geothermal heat provided the driving force that allowed reactions to proceed. One of the simplest examples of this chemistry involves the formation of organic molecules, compounds that contain carbon and hydrogen, and often oxygen or nitrogen as well. Experiments conducted in laboratories have shown that when mixtures of gases resembling the early atmosphere are exposed to electrical sparks or ultraviolet light, they can produce amino acids, the building blocks of proteins, along with many other organic molecules. On the early Earth, lightning storms and solar radiation provided similar energy. In the atmosphere, simple gases were broken apart and recombined into more complex compounds, some of which fell into the oceans dissolved in rainwater. Over time, the concentration of these molecules in certain regions may have increased, especially in shallow pools where evaporation removed water but left dissolved substances behind. Coastal areas, where tides repeatedly flooded and exposed surfaces, may have been particularly important. When water evaporates, molecules become more concentrated, making reactions more likely. When the tide returns, it redistributes those molecules, allowing them to interact with new materials. These cycles of concentration and dilution could have provided a natural laboratory for chemical evolution. Another environment that may have played a crucial role was the deep ocean near hydrothermal vents. In these regions, seawater seeped into cracks in the crust, was heated by magma, and then returned to the ocean carrying dissolved minerals and gases. The boundaries between hot vent fluids and colder seawater created sharp gradients in temperature and chemistry, conditions that can drive reactions that would not occur in more uniform environments. Mineral surfaces themselves may also have been important. Certain types of clay and other minerals can act as catalysts, helping molecules assemble into longer chains. They provide structured surfaces where molecules can line up in ways that make bonding easier. In some cases, these surfaces can even help organize molecules into repeating patterns, a step that may have been important in the formation of early genetic materials. One of the most significant developments in this long chain of events was the emergence of molecules capable of storing information and making copies of themselves. Today, DNA carries genetic information in living organisms, but many scientists believe that an earlier molecule, RNA or something similar, may have played this role at the beginning. RNA has a remarkable property. It can store information in its sequence of chemical units, and under certain conditions, it can also act as a catalyst, helping reactions occur more quickly. In laboratory experiments, researchers have created RNA molecules that can catalyze the formation of copies of themselves, at least in a limited way. This suggests a possible pathway by which non-living chemistry could gradually give rise to systems capable of replication. Once replication begins, even imperfectly, a new process comes into play: natural selection. Molecules that replicate more efficiently become more common. Those that are less stable or slower to replicate become less common. Over many cycles, complexity can increase. It is important to remember that this process would have been extremely slow. Early replicating systems were probably fragile and inefficient, easily disrupted by changes in temperature or chemistry. Many would have formed and disappeared without leaving any lasting trace. But over hundreds of millions of years, small improvements could accumulate. At some point, groups of molecules may have become enclosed within tiny membranes, forming structures that resemble very simple cells. Fatty molecules, which have one end attracted to water and another repelled by it, naturally assemble into thin films in water. These films can form small bubbles, or vesicles, that trap other molecules inside. Such vesicles provide a boundary, separating internal chemistry from the surrounding environment. Inside, reactions can proceed in a more controlled way, and molecules that replicate or catalyze reactions can remain close together. This simple compartmentalization is one of the key features of life. The earliest protocells, if they existed in this form, would have been extremely simple compared to modern cells. They may have lacked many of the structures and processes we now associate with life. Yet even a simple system capable of replication, metabolism, and variation would have marked a profound change in the history of the planet. From that point forward, evolution could begin. But before reaching that stage, the Earth remained a world where chemistry dominated, and the boundary between non-living and living matter was still unclear. The oceans were full of reactions, some simple, some complex, all driven by energy from the environment. Organic molecules accumulated in certain regions, broke apart in others, and reassembled again in countless combinations. Meteorites continue to contribute to this chemical diversity. Many meteorites contain organic compounds formed in space, including amino acids and other complex molecules. When such objects fell into the oceans, they delivered new materials that could participate in ongoing reactions. Ultraviolet radiation from the sun also played a role. Without an ozone layer, high-energy light reached the surface more easily than it does today. While this radiation could destroy some molecules, it could also drive reactions that formed others. The balance between destruction and creation may have been an important factor in shaping early chemical evolution. Meanwhile, the planet itself continued to change. Continents, still small and fragmented, drifted slowly. Volcanoes built new land and released gases into the atmosphere. Ocean currents circulated heat and nutrients. None of these processes were directed toward creating life, yet together they created conditions in which life could eventually arise. It is sometimes tempting to imagine the origin of life as a single event, a moment when something suddenly crossed a boundary and became alive. In reality, it was probably a gradual transition, a continuum of increasing complexity. At what point does a self-replicating chemical system become a living organism? The answer may not be sharp or simple. What matters is that, over time, systems capable of sustaining themselves and reproducing became more common. Once that happened, the history of the Earth changed in a fundamental way. Living organisms began interacting with the environment, altering the composition of the oceans and atmosphere, and leaving traces in the geological record. But at the stage we're considering, that transformation had not yet fully taken hold. The Earth was still balanced on the edge between chemistry and biology, a world of storms, tides, and silent oceans where molecules were assembling, breaking apart, and assembling again. Night followed day. Tides rose and fell. Volcanoes erupted and cooled, and within the waters reactions continued patiently, guided only by the laws of physics and chemistry. Time remained the most important ingredient. Millions of years passed, then tens of millions, and the slow work continued. Eventually, somewhere in those ancient oceans, a system emerged that could truly be called alive, a microscopic organism capable of maintaining itself and reproducing. That step, small as it might have seemed, would set in motion changes that would transform the entire planet. Because once life began, it did not remain insignificant for long. Over immense spans of time, living organisms would alter the chemistry of the oceans and atmosphere, preparing the way for a world very different from the one that had existed before. Standing on the surface of the Earth today, it is almost impossible to sense how deep its history truly runs. The ground beneath our feet feels solid and permanent. Mountains appear ancient and unchanging. Oceans seem timeless as they rise and fall along familiar shores. Yet every rock, every grain of sand, every drop of seawater carries within it a history that stretches back billions of years to a time when none of these landscapes existed, when the planet itself was still forming and the conditions of its surface would have seemed utterly alien to us. Looking backward through deep time is not like looking back through human history. We cannot rely on written records or even fossils for the earliest chapters. Instead, scientists piece together the story from subtle clues preserved in ancient minerals, from the chemistry of rocks, from the craters of the moon, and from the physics of how planets form. Each piece of evidence is small on its own, but together they reveal a picture of a world that began in fire, cooled under endless storms, and slowly transformed into the planet we know. One of the most remarkable lessons from this long story is how dynamic the Earth has always been. It has never been a static world. From the moment it formed, it was changing, reshaping itself under the influence of heat, gravity, impacts, and chemical reactions. The continents we see today did not exist in the distant past. The oceans have changed in depth and composition. The atmosphere has been transformed more than once. Even the length of a day has not remained constant. When the moon first formed, Earth rotated faster, and days were much shorter than they are now. Over billions of years, tidal interactions between Earth and Moon have gradually slowed the planet's rotation, lengthening the day little by little. It is a reminder that even something as fundamental as the rhythm of day and night is not fixed forever. Another lesson is how interconnected the systems of the Earth have always been. The atmosphere, oceans, crust, and interior do not operate independently. Changes in one affect the others. Volcanoes release gases that shape the atmosphere. Rain dissolves minerals from rocks and carries them to the oceans. The oceans absorb carbon dioxide and influence the climate. Heat from the interior drives tectonic movements that reshape continents and ocean basins. These interactions were already underway in the earliest ages of the planet long before life appeared. The Earth was, in a sense, preparing itself, creating environments where water, energy, and chemistry could interact over long periods. Stability did not come from stillness, but from the balance of many changing processes. It is also striking how much of the early Earth story is preserved in unexpected places. Tiny crystals of zircon, some more than 4 billion years old, contain chemical signatures that reveal the presence of liquid water at a time when the planet was still very young. The heavily cratered surface of the Moon preserves a record of impacts that once struck the Earth as well. Meteorites that fall today carry materials formed in the earliest days of the solar system, offering glimpses of the conditions from which the planets emerged. These fragments of evidence allow us to reconstruct events that no one witnessed, to understand processes that unfolded over spans of time far longer than human experience can easily grasp. Thinking about deep time changes the way we see the present. The continents, which appear permanent on human timescales, are actually drifting slowly across the surface, moving a few centimeters each year. Mountains rise and erode, oceans open and close. Given enough time, the face of the Earth changes completely. The climates of the past have also varied dramatically. There have been periods when the planet was much warmer than today, and others when ice covered much of the surface. The balance between sunlight, greenhouse gases, and geological processes has shifted again and again, producing a wide range of conditions over billions of years, and yet despite all these changes, certain patterns remain. Water has been present on the surface for most of the planet's history. The magnetic field has protected the atmosphere for billions of years. Plate tectonics has recycled crust and regulated the climate over immense timescales. These long-term processes have helped maintain conditions that allow complex systems, including life, to persist. Looking back at the earliest ages also reminds us how unlikely some aspects of our world may be. The formation of a large moon, the presence of abundant water, the balance of greenhouse gases, the protective magnetic field, and the steady brightening of the sun all played roles in shaping the Earth's environment. If any of these factors had been significantly different, the planet might have followed a very different path. Mars, for example, appears to have lost much of its atmosphere and surface water as its interior cooled and its magnetic field weakened. Venus, though similar in size to Earth, developed a thick carbon dioxide atmosphere and surface temperatures hot enough to melt lead. The differences between these worlds and our own illustrate how small variations in initial conditions and long-term processes can lead to dramatically different outcomes. Another insight from studying the early Earth is the importance of time itself. Many of the processes that shape the planet required millions or billions of years to unfold. The formation of continents, the accumulation of oxygen in the atmosphere, the evolution of complex life, all depended on long periods of relative stability punctuated by occasional disturbances. On human timescales, change often feels rapid and dramatic. On geological timescales, even the most significant transformations are gradual, the result of countless small steps accumulating over immense spans of time. It is also worth reflecting on how much of the Earth's early history remains uncertain. The rocks from the first few 100 million years are rare, often altered by later processes or destroyed entirely. Scientists continue to search for new evidence, refining models and testing hypotheses about how the atmosphere formed, how oceans accumulated, and how life began. This ongoing process of discovery is itself part of the story. Each new measurement, each new mineral analysis, each new observation of other planetary systems adds to our understanding of how worlds form and evolve. The study of the early Earth also helps us understand other planets. Observations of distant stars have revealed that planetary systems are common in the galaxy. Many of those systems may contain rocky planets similar in size to Earth, some perhaps with oceans and atmospheres of their own. By understanding our planet's past, scientists gain insight into how such worlds might develop and whether they could support life. In this way, the history of the Earth is not just a story about one planet, but part of a larger story about how planets everywhere come into being and change over time. There is something quietly humbling in this perspective. The mountains, forests, and oceans that seem so enduring are only temporary arrangements of matter, shaped by forces that have been at work for billions of years and will continue long after human history has passed. The continents will drift, the climate will change, the sun itself will grow brighter over hundreds of millions of years, gradually altering the conditions on the surface. Deep time stretches both backward and forward, far beyond the span of any single species. And yet, looking back at the earliest Earth also highlights something remarkable about the present. Out of a world that began as molten rock, shrouded in steam and bombarded by falling worlds, conditions emerged that allowed life to arise, evolve, and eventually become capable of understanding its own origins. The rocks, oceans, and skies that once existed without life are now part of a living planet, one where organisms influence the atmosphere, shape the landscape, and leave traces that will endure in the geological record. Every breath we take depends on processes that began billions of years ago, from the formation of the atmosphere to the evolution of photosynthesis. Every drop of water we drink has been part of the Earth's long cycle, evaporating, condensing, freezing, melting, and flowing again countless times. Even the ground beneath us contains minerals formed in ancient oceans, volcanic eruptions, or the slow cooling of magma deep underground. The past is not separate from the present. It is built into the very substance of the world around us. Thinking about these vast stretches of time can be strangely calming. The worries of a single day or even a single lifetime seem smaller when placed against the backdrop of billions of years. The Earth has endured collisions that reshaped its surface, climates that transformed its oceans, and changes in atmosphere and geography beyond anything in human experience. And through all of that, it has continued to change, to adapt, to evolve. There's also a quiet sense of continuity in realizing that the same physical laws that shaped the early Earth are still at work today. Gravity still pulls, heat still rises, rocks still weather, oceans still circulate. The processes that built the planet have never truly stopped. They have simply slowed or shifted in scale. Somewhere deep beneath the surface, mantle currents still move slowly, carrying heat upward. Volcanoes still release gases that become part of the atmosphere. The moon still raises tides, just as it did billions of years ago, though more gently now. In a way, the young Earth is not entirely gone. Its influence remains in every eruption, every shifting plate, every drop of rain that falls and flows toward the sea. And when we look up at the moon, we're seeing a companion formed in one of the most violent moments of the planet's history, a reminder of a time when worlds collided and the sky itself was filled with fire. The story of the Earth's beginning is not only about the past, it is also a way of understanding the present and imagining the future. Planets are not static objects. They are evolving systems shaped by forces both internal and external, changing over timescales far longer than human experience. As the sun continues to brighten in the distant future, the balance that allows oceans and life to exist will eventually shift again. The Earth will not remain exactly as it is forever, But that transformation lies far ahead, beyond spans of time so long that even the oldest mountains of today will have come and gone. For now, the planet continues its slow, patient evolution, shaped by the same processes that began when dust gathered into a world, when oceans formed from endless rain, and when chemistry and ancient waters took its first steps toward life. And somewhere beneath the quiet movement of clouds and tides, the echoes of that distant past are still present, written in stone, carried in water, and reflected in the steady light of the moon that rises night after night, just as it has for billions of years,